we are going to talk about that a bit more in detail on day 3, where I'm gonna make a presentation showing you what are the main findings and what are the works that are still going on. But now I can just list here what are the main activities for each of the work packages. So work package 1, work package 1 was about acid mine drainage and investigations of different methodologies to reduce acid mine drainage. Work package 2 was about geotechnical and geochemical analysis of tailings, and we have evaluated also tailings behavior under triaxial tests in CT scanner, and we also have characterized several tailings type, and in particular bauxite residue. Then work package 3 was about numerical modeling. We have worked back calculating Fundau failure, and then we have worked with probabilistic stability assessment. Work package 5 was about using INSAR technology and then using the inverse velocity to try to monitor the formation of tailings dams and perhaps predict. And work package 5 was about runout modeling, together with also statistical analysis of tailings dam failures. And now, before diving into the workshop and make the most out of this opportunity, I'm just second what Dominik has said already. So I want really to extend my deepest gratitude to the sponsors who have made this event possible. And moreover, I'd also like to express my appreciation to my colleagues because their support and dedication has been very important, fundamental in bringing this workshop to life. I guess all of you have kind of been in contact with Sparsha, and she has helped a lot as a contact person for speakers and attendees, as well as helping with many practical aspects. Dominik, who is the Natural Hazard Director, and Håkon, who is section head, they have provided administrative support, and then Maren and Caroline took care of the communication, and Kirsten about logistic and practical aspects. Well, as maybe you don't know, but Dominik was mentioning that, but there are over 100 people participating in this conference, in this workshop. Most of them are here, but many are online because this event is streamed in real time. And there are more than 20 nations represented here. So in the next 3 days, we'll share expertise, best practice, and innovation with the aim of moving towards safer tailings dams. So it's our diverse group includes experts from various fields, nations, expertise, offering a unique mix of perspective. So in my mind, it's more or less something like this, right? I don't expect you to fight, though. But this diversity will enrich our discussion and hopefully will pave the road for innovative solutions and collaboration. Throughout our session, we'll encourage really active participation, networking, questions, discussions, because it's really important. It will help us, everybody of us, to improve and to learn more. So your presence here demonstrates that your commitment to this cause it's important, and that together we can make, hopefully, a difference. Now, before we begin, I would like to start with this question. What we can do collectively to ensure safer and more sustainable tailings dams? This was our question at the beginning of the 4-year research project. And to try to answer this question, we decided to structure our workshop in these eight sessions. So 4 in day 1 and 4 in day 2. So the first 4 sessions are advances in lab testing for tailings, then site characteristic, numerical modeling of tailings dams, runout modeling, and seismic design. And then in the afternoon, for people from Scandinavia, there will be the ICOLD Nordic Tailings Network meeting. Day 2, same venue, other 4 sessions, remote monitoring and geophysics, acid mine drainage and environmental issues, industry challenges, standards and guidelines. And then there is a closure speaking about future of tailings dams, reflections from the 2 days of workshop. Then for the people attending in person, there is also an extra bonus, which is day 3. Day 3 will be at NGI. And we are going to have a presentation about this strategic project, this research project I was describing you in the first 2 slides. This will be at NGI, as I said. Then you will have the chance to visit our labs. And then there will be roundtable discussions with participants and speakers. And then there will be a lunch at NGI. Well, thank you all for joining us at this tailings dam workshop. Let's get started. I may ask Sparsha to... we are 10 minutes ahead of time, okay, but we can just start with. Wanna take a break? Okay. We can take just 10 minutes because we have 10 minutes. We are 10 minutes in advance, so we don't want to mess up the schedule, and in particular for the online people. But I can mention that convening these 2 days, there will be myself and Sparsha, and we will let the speakers know when they have 3 minutes left. We really will take care of the timing. Our director is German, and then we cannot make mistakes here. Okay, thank you very much. We'll reconvene in 10 minutes.
Hi. So, very good morning to all of you. This is Sparsha Nagula. I think a couple of you have been in contact with me. So finally, we meet in person and online. So without wasting any more time, let's begin with the first technical session, which is advances in lab testing for tailings. So before we talk about tailings, in detail, we need to understand what tailings are. So the best way to do it is to understand how they behave in the field and also put them into the laboratory. So that's what the first session talks about. So as the first speaker, we have Jorge Macedo from Georgia Tech, USA. So he's an assistant professor with 10 years experience in geotechnical earthquake engineering, numerical modeling, risk assessment, and mining geotechniques. So the floor is yours, and you have 20 to 25 minutes to go.
Thank you, Sparsha. Good morning, everyone. It's a pleasure to be here. Thank you for inviting me, and thank you very much to the organizers. Let me just put my timer, otherwise I'm going to be running out of time. So, okay, here we go. Well, my talk is going to be about 25 minutes. I'm going to be discussing on the mechanical response of mine tailings at different scales. So a quick disclaimer, it's not going to be only about lab testing, but it's going to be having lab testing, but more stuff as well. So let me get into that. First of all, the projects that are associated with this presentation are listed over there. So there are 3 projects. The first one is a static liquefaction of mine tailings under non-standard stress pads. The second one is towards the next generation of data-driven and performance-based multi-scale procedures in mining geotechniques. These 2 projects are funded under the National Science Foundation. And I will be also including some material from active projects we have at the Tailings and Mine Waste Engineering Research Center that I lead at Georgia Tech. So very quickly, oops, this is going backwards. Very quickly, let me tell you about Tailings in 1 minute. So Tailings is a research center that is a consortium of faculty at different universities, including Georgia Tech, Colorado State University, UC Berkeley, and Illinois Urbana-Champaign. Indeed, we are organized, as it is shown on that slide. We have a steering committee that is formed by myself, I'm the chair of the center. Chris Vareithier from Colorado State is also on the steering committee. Jonathan Brain from UC Berkeley, and Scott Olson from Illinois Urbana-Champaign. We have also an advisory board. I think if there is something we are proud of at Tailings is our advisory board that is amazing. We have people from the industry and also from academia and expert leaders on the tailings industry. So we have also regular members. The idea of the regular members is that they bring multidisciplinary expertise, because the steering committee is more having a geotechnical expertise. So as you may know, tailings projects are quite multidisciplinary. So we bring actually that multidisciplinary aspects through our regular members. We have also business industry partners that are actually the companies that support our work. We wouldn't be able to do what we do without their support. So they are essential for all the research and educational activities that we do. And we have also affiliate organizations like the United States Society of Dams that pretty much share our mission of I would say making mining infrastructure resilient and also create the next generation of tailings engineers. So having said that, let me start to get a little bit more into the meat of this presentation. First of all, a very, very quick overview of tailings. Typically, we are going to be seeing tailings in different ways. For example, on the, let me see if this has a pointer. Okay, perfect. So for example, over here, these are the so-called conventional tailings, where there is, I would say, the proportion between water and solids is kind of 70 to 30% maybe. Then if we start to make, I would say, to take water out of the system, we can be getting a thickened tailings. Then we can get a paste, and we can go even into a filter tailings. So from a geotechnical perspective, tailings are quite interesting because they are usually in the silt gradation. And in geotechnical engineering, I believe we have a decent knowledge on sands and clays, and even I would be saying quartzitic sands and clays with typical mineralogies. Comparatively speaking, we don't have, I would say, the same knowledge on silts. Another aspect that is very interesting on tailings is that they are pretty much man-made. That means that they are thermodynamically unstable compared to natural soils. And they are also presenting phenomena like early diagenesis, for example, that's going to be influencing fabric and so on and so forth. So there are many reasons why tailings are quite interesting. These are just a few of them. So now I think this was mentioned on the introduction as well, but yes, as a background for the motivation, here I'm showing you a couple of charts. Here on the top, you can see how much minerals you need for an electric car and how much for a conventional car. This is just to send a message that to go into the green revolution and also all we need to do related to climate change and everything, mining is just essential. Mining is going to be key. So we can look at that also with these charts over here. For an offshore wind, you need about 13 times the minerals you will be needing kind of for a size gas fired power plant. So mining is essential, and we will need that in the future. So tailings is directly related to that. So now getting a little bit more specifically into the content of this presentation. So our projects are under the umbrella of performance-based data-driven procedures. So for that, let me define very quickly what is performance-based engineering, which is the design, evaluation, and construction of engineering systems that meet as economically as possible the uncertain future demands that are often related to extreme loading events or owner, user, and nature. So, and this, just to mention something else, the new standards on tailings are also promoting performance-based engineering. So in that context, what we have been doing is generating and collecting information at the micro scale, at the lab scale, and also at the field scale. We collect all that information, and we are actually focused on using modern data science and artificial intelligence techniques in order to know as much as we can. I'm talking about supervised methods, unsupervised methods, reinforced methods, active learning, and so on and so forth. We have to be careful, though, with artificial intelligence, as I will be elaborating in a little bit. The final goal is to generate the next generation of data-driven PV procedures for tailings, storage facilities, and the ultimate goal is to have safe enough systems under low enough accepted risks. So what we have been doing at Tailings is, and also with the NSF project, is on a first stage to generate and collect information. So I'm going to be walking you through what we have been doing at the micro, lab, and field scales. So first of all, we were working for about 4 years on creating a mine tailings database. I'm showing you in this slide just what is a class A. So we have different classes depending on the information that we have. On a class A, we have microstructural information, we have index tests, comprehensibility information, strength information. Typically, we include strength information only if we have a critical state line defined. We have strength information. We do also a lot of cyclic stuff because of the seismic component of that. For South America, for instance, seismic is very important. We have field information in terms of CPTU. We have also geophysical information and also vendor element test. We have also small-scale information with mini calibration chambers, for example. And we have been looking through one of the projects at Tailings also on the unsaturated aspects that are quite challenging. So we have also soil water characteristic curves. So now, I would say this slide summarizes a little bit the idea of what we have been generating. For example, here you can see the ranges of the particle size distributions for the tailings that we have into our database. We have been generating microstructural information for them. You see here an SEM example. We have also CPT data for those. Here, the QT, the tip resistance, is just plotted for the full range with the average in the middle, but that's just to give you an idea of all the range that we have for CPT information in that case. This is the range of critical state lines that we have, and this is the range of cyclic resistant curves that we have for liquefaction purposes, for example, in terms of cyclic loading, and this is giving you an idea of the range of vendor element testing information to define stiffness and how it is related to confinement. So ultimately, what we want to do is to extract key mechanistic information for engineering applications, and also we want to discover high-level interactions using artificial intelligence. So I'm going to walk you now a little bit more through the three different scales I was mentioning. For example, at the micro scale, we have generated significant information on SEMs. This is just an example of a fine tailings. This is an example of a coarse tailings. And we have been also generating X-ray micro-CT information, which I have to say is very challenging for tailings if you are doing it, I would say, in a robust way, is very challenging because the size of these materials could be in the order of 3 microns. If you really want to do segmentation with that, it's going to be challenging. We literally suffer a lot in order to get into, I would say, a segmentation that we were happy. So we have ongoing collaborations with the École de Pont University at that scale. So we have also generated information at the lab scale. So during the last 5 years, we have built a very nice laboratory at Geotech where we have all of these devices. We have resonant columns, hollow cylinders, plane strain, triaxial, simple shear, torsional shear, and also calibration chambers at different scales. And what we have been doing is taking our tailings, these are just examples of some gradations, and we have been reconstituted them with different procedures. Reconstitution could be a whole topic on its own, so it can have a lot of caveats. So but you can learn a lot about the, oops, let me put that. So you can learn a lot from different fabrics and so on and so forth. So what we have been doing mainly with that laboratory information is to focus on the phenomena of static liquefaction, which is just an undrained loading instability. There is nothing, I would say, Mike with that. So I'm taking these figures from LADE 1999 just to remind you what is static liquefaction about. So typically here you are seeing 3 stress pads, undrained triaxial stress pads. If you take the tip of these stress pads and you join them, you're going to be defining a region of potential instability. So if you take one of them and you just plot the deviatoric stress and axial strain, typically you will be saying at the lab scale that static liquefaction is going to be happening here at the peak conditions. This is under undrained loading, but static liquefaction can be also happening. Hopefully the video is going to be helping me. And let's see if that is running. Seems that it is not running. Anyways, you can see the video on that YouTube link if this is, it seems that it's not working. Apologies for that. But in any case, this is a CSD stress pad that is purely drained. Let me see if I make it work. OK, better I don't mess up with the technology and I just keep going, OK? So this is a CSD stress pad. Oops. Let me see what's going on here. OK, here we go. OK. Anyways, this is a CSD stress pad where you typically will be having an initial drain triaxial stress pad over here, and then you have kind of sort of a stress relief. And typically, you will be seeing that instability is going to be happening in the middle of that stress release, and that's going to be manifested with very large deformations. So in that video, pretty much what you will be seeing is that this test initially is not even moving, and eventually it's just collapsing like very abruptly. OK, so sorry that the video is not playing. So now something that I wanted to share is that we have pretty much extracted all of that information and we have interpreted the information. And I'm showing here just one example highlighting the role of comprehensibility. I decided to highlight that role because, in my opinion, it's not emphasized enough when we are dealing with liquefaction aspects. As a matter of fact, when we deal with cyclic liquefaction, it's not even considered. Typically, it's just fine contents, what is considered. So here what you are seeing on the left, this is the undrained shear strength, and this is the state parameter. In green, you see the range of sands. This little kind of sand over here was a silty sand with more compressibility, so that's why it is outside of this range. And then you see the range for tailings, which is kind of quite broader. Now, if you bring comprehensibility into the picture by normalizing the state parameter by the slope of the critical state lines, now you get kind of a much narrower range. And this is consistent with critical state soil mechanics framework and also consistent with the sand response. So pretty much, we have done analysis like this. This is published already in Macedo and Bergaray 2022, which is in the Canadian Geotechnical Journal. And the conclusion is that the response of mine tailings is consistent with critical assay soil mechanics, but there is a different scaling compared to sands, for example. And that, at the end of the day, that just sends the message that common correlations should not be taken as applicable to mine tailings without really thinking about it. The scaling is going to be different. The framework is suitable, but the scaling is different. So now, something that we have been looking at is also fabric anisotropy. And here, pretty much, I was posting a question if it is important. If you look at a typical, failure surface, this is, for example, I just took that from the Fundao panel report. So you will be seeing that depending on where you are at in your failure surface, you're going to be having different state of stresses, compression, simple shear, extension, and so on and so forth. So to reinforce that message, I love these figures over here. Those are taken from Yoshimine et al. I want to just get your attention on this test over here and this test over here. This is a triaxial compression test, and this is a triaxial extension test. So all the conditions for these two tests are exactly the same. Initial void ratio, initial confinement, everything exactly the same. Only the loading mode is different. But take a look to the response. It's quite different, and probably is going to be even clearer if you look at that in the stress-strain response, where you see that for a triaxial extension, there is going to be a significant drop from peak conditions to residual, and on the triaxial compression, there is less. So yes, because of the loading mode. But it's not only that. If you start to take a look to, this is data from hollow cylinders, where pretty much there is a vertical loading that is deviating from the vertical direction. And there is also an intermediate stress that is applied over here, V 0.5. V is a parameter used for intermediate stresses. So what you can see is that pretty much very comparable initial conditions, but you will be seeing that the softening response is going to be increased as you increase alpha, as you increase the deviation of the vertical. And that's going to be depending on what is your initial fabric. So we have been working numerically on that, on those aspects, and also incorporating the effect of inherent fabric. So we have two types of fabrics, the inherent and the induced, that we have been including. So here you see an example of the results. These are experimental tests that were generated by others using a slurry deposition and moist damping. And we have been simulating them numerically using bonding surface plasticity and using fabric as well as a parameter. So pretty much it is well known that at the lab, if for moist damping, you have a less initial, I would say, fabric intensity compared to slurry deposition. And we can, with the same set of parameters and everything the same, we can reproduce, I would say, reasonably well the difference. Something else that we were putting forward on that direction is also the concept of the instability surface. So as I said before, a few slides ago, this is how the typical definition of a static liquefaction will be looking like. But if you go into a multi-stage, I would say, setting, this is the pipeline, you're going to be seeing a surface. If you, for example, this is for an alpha 45, that just means that the vertical load is inclined 45 degrees respect to the vertical. And then we considered all the load angles around the pipeline. But something that is interesting here is there is previous research that was looking into that, but without considering fabric. When you don't consider fabric, this is going to be symmetric. It's going to be a symmetric surface. When you bring fabric into the game over here, that's not going to be any more symmetric. So now your initial fabric and how your loading and isotropy is happening is going to be changing things. So that's very interesting, in my opinion. So with all the laboratory data that we have generated, we have also calibrated all that data with numerical, with constitutive models. Why we have done that? Well, in order, the motivation is pretty much that the mechanistic-based constitutive models can capture tailings response, including a static liquefaction. So we want to parameterize the responses that we are seeing through some other parameters that have a physical meaning. For example, we use Norsand. Norsand is very nice because most of its parameters, and Mike is going to be here, so he may be talking about that later, most of its parameters can have actually a mechanistic meaning, which is very nice. So we have been also using other models, for example, bonding surface plasticity, you can see the responses over here. But not only that, we have been also looking into induced anisotropy. You have some experimental tests over here, on the left, and you see some simulations here on the right. So pretty much what we are going to be doing is using the parameterization of all of these, mechanical properties in order to come up with something based on AI. So hopefully this video now is going to be working. Yes. So this is working. This is just to show you. I wanted to share that we created these educational tools for Northsand. You can see that everything is on this link below. So something that we found is that there was kind of a learning curve for Northsand. So my student Vivek, Srinivas, and I, we put kind of that tool. And this is, for example, this was a drain triaxial test. Let me go to the next one that probably is going to be more interesting. Let me see. OK. This one, for example, this is going to be a static liquefaction. So it's nothing but just one facet of the mechanical response. This is Northsand and how it is behaving. I don't have the time to go into Northsand. And this is just the numerical simulation. I'm leaving this just for reference. So then let me switch to the other scale that's going to be the field scale information. On the field scale, this is the CPT data that we have generated. For this presentation, I have opted to only talk about CPT. Something I want to highlight is that there is significant layering and spatial variability when you do a CPT in a tailings storage facility. This is shown over here, and it may be clearly, distinguished over here. You see significant layering. So it's not just about having very homogeneous layers or samples in the lab. Yes, you learn from that, but the reality is that on the field, this is going to be very layered. So it's not as simple. So similar to the lab testing, we have been conducting numerical simulations to simulate all the CPT information we have at the field and also the mini calibration stage. This is just an example of a couple of them that I wanted to show on drain behavior and undrained behavior. Notice how the excess pore pressures are generated over there. We have been also looking at the spatial variability issue. In the case of spatial variability, we started our work with natural soils, but I think it is interesting to share what we've done because it can be also applicable to maintenance. We have created random fields. A random field is pretty much, I would say, our mathematical description of spatial variability. We created that, okay? We imposed that in the computer. And then, through 3D printing, we replicated that field. So we printed that. You can see some of the printed specimens over here. And the next slide over here is showing that in a 3D. You can see how it is printed. This is our, I would say, our target, what we designed on the computer. And this is what we printed on the specimen. So it's a quite nice match. So what we were doing with that, we were kind of sampling, I would say, the printed specimens. You can see here a little tiny sample over there. This is just an example of a torsional rear shear rheometer that we were doing. This was to, it's kind of an analogy to a resonant column test. We did that for defining stiffness parameters. So we were, this is also published, by the way, on soil dynamics and earthquake engineering if you're interested. So the idea was to sample, the printed specimen, and then from that we conduct tests and we try to understand what is the role of spatial variability over there. All of that is going to be integrated into performance-based engineering. And just to show you an example of that. So what I'm trying to say is everything we learn from the micro scale, lab scale, and field scale, all of that can be integrated into performance-based engineering. And here I will be showing you just the details are going to be showing up in a paper at the ASC journal that's going to be showing up. This is already accepted. We did that exercise for the CADIA failure just to showcase some concepts. And here what I'm showing is just, how the evolution of the normalized stress ratio compared to the stress ratio you need for liquefaction is evolving. So if this number is close to 1, that means that liquefaction may be triggered. So in this case, we did that to just, I would say, replicate what the panel did. But something that was new was we did what I believe is the first. Oops, let me see. Hopefully the video is going to be working here, because that's a nice video. Yeah, it's working. So we did also a post-triggering assessment where you can see the CADIA failure. This is kind of trying to capture the run-out distance. So it was quite nice, I would say, in my opinion. Here you can see the real geometry after the failure, and you can see here the simulated geometry. Now, just to finish my presentation, I want to put some topics for discussions. So first of all, we are on the era of data. So if you look at how much data is generated every day, so you are going to be seeing, for example, 500 million tweets per day. Well, it's not anymore Twitter, it's X now, right? It has changed, but you see that there is a lot of information. And I wanted to show you this chart also from John Naisbitt that is showing how data has been increasing over the years. And I wanted to share this quote also. We are drawing in information, but starve for knowledge. So we have a lot of data, even from our tailings storage facilities. We're collecting a lot of data, but we really need to make sense of that data. And now, in order to do that, you know, let me do this little exercise very quickly. Let's say that you have something that you measure in the field and something that you want to estimate. And these are the dots. This is just any random data. Usually, I show this chart to my students, and I ask them, pick up one. Pick up what is the best model. Is it this one, this one, this one? Pick up one. Because, you know, with machine learning, artificial intelligence nowadays, you can have any of these models. Typically, what they say is, I don't know which one to pick, but I do know that I don't like this one over here, the house of cards. And typically, they say, because, you know, within the area where I have data, it's kind of quite nice, but outside of that, it's just crazy. And that's actually very important because machine learning typically is going to be good at interpolating things where you have data, but it's not going to be as good as extrapolating things unless you bring physics into the problem. So now there is an emerging field that is physics-based machine learning, where you can actually take advantage of the data you have, but you can bring physical principles into that as well. So there is a word of caution over there. We need to bring physics and mechanics. Machine learning alone can be pretty much a black box if you are not aware of that. And in order to do that, let me also bring another idea over here. Yeah, this is for discussion again. So and let me describe the chart very quickly. First, this is a chart from my colleague Paul Main at Georgia Tech. I love Paul. He's great, and I think he has very good connections here at NGI. So this is the relative reliance, and this is the year. This is kind of a chart trying to describe geotechnical engineering. You see SPT, outer upper limits. You see how lab testing was evolving, in situ judgment, and judgment is always important, analytical models, and so on and so forth. He initially put critical state soil mechanics here as a niche. And I love Paul, but I disagree with putting critical state soil mechanics as a niche over there. And I would say what I would like to put forward for discussion is that, in my view, critical soil mechanics should be used actually as the framework to join these different scales. You can use critical state soil mechanics to aid in the interpretation of your in situ testing, also your laboratory testing. You can build analytical models, cavity expansion, an example. You can have numerical simulations. Many of the robust modern constitutive models are based on critical state soil mechanics principles. Nowadays, we have high-performance computing. If we run thousands of these models, we are going to be generating the data for probabilistic models. We have machine learning, we have AI, and so on and so forth. So at the end of the day, pretty much going back to the idea on the previous slide, if you use artificial intelligence and you bring physical principles through critical state soil mechanics, probably that's going to be a very interesting path forward. So, and last but not least, just a quick reflection on education, because I think I'm working now at a university, so that's important for us. So I think we should be really thinking on a forward-looking education for educating the next generation of tailings engineers. There are ongoing efforts on that at Georgia Tech and Tailings that I'll be happy to share during the discussions. But I think the idea is to have holistic engineers that are very strong on mechanical concepts and very strong engineers, but they also are equipped to address grand challenges, and they are developing entrepreneurial mindset, and also they are engineers who habitually create value for society, which is very important for these days. With those topics for discussion, so I will be finishing up over here, and thank you very much.
Thank you, Jorge, for the nice first starting off talk. I think that was a soft introduction into tailings. So Jorge managed to introduce everything from lab scale testing to physical test to numerical modeling to runout analysis, and also has raised questions of what we should be discussing. I do not see any questions from the people online. So again, drop in a request that if you have any questions for the speakers, just mention the name of the speaker and drop in your question, and we would try to answer that. But now the floor is kind of open to the audience with us. So do you have any questions? Looks like it's a bit of a slow start. You people need more coffee. Yeah. How can? Maybe you should use.
Yeah. It can be also a jet lag. It's
Yes.
2 a.m. in my brain.
Yeah. Thank you so much for a very comprehensive presentation. I was just a question which is not directly mentioned. Maybe, are we able to sample silt from the ground and take it into the lab, and that all represent what we have in situ? How can we prove that?
Yeah, I think that's a very good question. It's very difficult to sample those materials, but I probably can share the experience on, well, actually on the introduction session, there was a reference to a paper that was produced here at NGI for sampling silts. That's a very nice, I think, reference that could be providing some information on that. I can share the experience on New Zealand as well. On New Zealand, we were using the Dames and Moore sampler, that is a hydraulic piston sampler. I would say the performance was, in our opinion, it was good. Probably, if you want to really judge if that is representative of the field or not, there are different procedures that are used on engineering practice, like measuring shear wave velocities and so on and so forth. But probably if you want to really maybe look into that deeper, maybe you can look at the microstructure of something that has been sampled. Here, I think at NGI, Santiago Quinteros has done something related to that with frozen specimens, and then you can reconstitute them. You can take them to the lab, and you can maybe with X-ray microcity take a look at that in a very fundamental way. So I'm sorry that I don't have, I would say, an answer saying, yes, it is definitely possible, but I would say, at least from my perspective, in terms of research, is very, very interesting. There are efforts that are going on that direction, but at least to my knowledge, there is no something that is very conclusive. But it's very tricky, kind of getting silts from the field. There is another question, I think.
It's Mike here. Jorge, it's not a question for you. It's a response to the previous question. My response to it, you cannot do perfect undisturbed sampling of silts. What I tell my people, and I will show you a slide when I come to my presentation, but just getting ahead of that, measure the bulk density of the sample you retrieve, measure your as-tested density or as-tested void ratio, and then use numerics to calibrate what you test, and then take the void ratio change to back out what you got in situ. Anyway, I'll talk to that more in my own presentation.
I would like to know your opinion about the existence or not about the quasi-steady state. So you are talking about critical state. However, in your figures, you have shown peak, minimum strength, and then dilation. And you're not saying anything about what happened at the end. So critical state is the minimum strength, or is the maximum strength that you're getting at very large deformation? That's my question.
Very large deformations. Yeah, so we define the critical state as the very large deformations. There is a quasi-steady state line that is at the drop, I would say that at the lowest point, but that's going to be fabric dependent. So depending on what's the fabric you have, you may be having different quasi-steady state points. So not sure if that's answering your question, Ramon. Well, you can use, it depends on what you are doing, right? So if you are, depending on what is your application, sometimes at the lab scale it's going to be difficult to get to the critical state. So depending on what is your design criteria and so on and so forth. So let me rephrase that. So at the lab scale, so you can see the peak and you can see the drop from the peak to quasi-steady state conditions, and then you can see the critical state at very large deformations. But that's going to be, I think, in my opinion, at the lab scale. If you go to the field scale, I believe it's going to be very difficult to go from the quasi-steady state to the critical state. So I don't see why you can have hardening at the field where you have all of this, very mixed mix of materials, a lot of dynamics and so on. So it's going to be very difficult. As a matter of fact, if you look at if you look at Mike's book, there is going to be, when they are looking into case histories, typically, for even with Northsand, the idea was to consider, the lowest point in the stress strain curve. Because at field conditions, you may not have actually the conditions to recover after that. On the lab, yes, you can, I think, look at that. There are a lot of publications that are looking at quasi-state and then going to the steady state, but I think the question is if that's realistic for field conditions. My opinion is that it's not.
Sorry, but finally, so you believe in the strengths developed at large, that you don't care about the minimum?
No, what I'm saying is at the lab scale, you can see both of them. Now the question is which one you use for design on the field. And I will be using the minimum one. The minimum? Yes.
Okay, so we also have some questions online. Luis asks you that, do you get pore water pressures developing in the CST path test?
Oh, yeah, that's a very interesting question. The short answer is it depends on the material and it depends on the rate of stress relief. So when we we did this test, the CSD test, we did it with tailings that were having about 90% fines. So in those cases, when we were doing a stress relief that was relatively fast, yes, we saw some pore pressures generated after the instability.
We have another question. Sometimes we have a lack of observational data for such cases. How can we improve the performance of statistical models, specifically when we talk about machine learning?
Yeah, I think, in my opinion, at least very big mining companies, I believe the data is available, in my opinion. They have a lot of instrumentation and information. I think one of the challenges is if that data can be used or not, because there are many, issues around that with the insurance companies and so on and so forth. So I think the data access is one of the challenges, because the data, again, in my opinion, is there.
So if we do not have any more questions, we can move on to the next presentation.
Thank you very much,
Jorge, for your first presentation. And so now we have Yusuke Suzuki from NGI. So he has been a geotechnical engineer with an experience of over 8 years, specifically working with laboratory testing. And he has a lot of experience working with tailings too. And he has a PhD from the University of Western Australia. So the floor is yours. You have 20 to 25 minutes to go.
Yes.
Yeah.
Thank you. Okay. Let me go back. Okay. Hi, everyone. My name is Yusuke Suzuki. Thanks for the introduction. Thanks for the first speaker, Jorge. It was comprehensive kickoff presentation. It was really great because I'm going to be talking about a little bit related, of course, in terms of lab testing part. And my topic will be, oh, here. Okay, sure. Will be on the lab testing on the tailings at NGI. I'll be presenting on behalf of our colleagues. We have some names here. I would just like to mention Santiago, Camelia, Diana, you're here, and Shin as well. So I will be talking about recent and the future research activities we have been thinking of. And the agenda for the presentation will be something like this. It's difficult. Can I stand here?
We are using online. We need to have you here.
Okay, so it's.
I can try to help.
Yeah, that's great. Thank you. Yes. So I'm gonna start with some introduction. Like I would like to introduce our facility at NGI first. And then I'm going to be moving on to the research activities, recent and the future. So along the way, I will talk about future research potentials. So maybe we can discuss those things towards the end. Let's start. So NGI has global labs around the world, here in Oslo, and one in Houston, Texas, and also Perth, Western Australia. I'm going to be talking about Oslo in the next slide, but in Houston, we also have relatively large facilities in Houston, and we have about 15 staffs working there, mainly working on offshore energy sections, but also tailings projects they have been working on as well. And that was acquired in 2016, but at the same time, we have now developing a new lab in Perth. As you see the photo, it's quite new, and we would like to launch that lab pretty soon for the local society. So then I will come back to the Oslo, and I found this picture. I thought I would like to show this because it's, of course, way before my time, but it's very nice to see how it has been developed at NGI. This picture is coming from 55, as Dominik mentioned. The NGI has started 53, so right after opening of NGI, we have already kind of established the lab. And since then, we have, until last year, I would say, we had very big open space. Maybe some of you may have been here, including the soil lab and rock lab in one space. It was great kind of atmosphere, I would say. But at present, I don't know if you know those things, but we have moved to a temporary space at the moment, and we have been having a little bit smaller rooms. Sorry. But our labs includes geotechnical soil mechanics lab and rock mechanics, and also we have environmental lab together with workshop and model testing areas. So we have about, I think, more than 45 staffs working in the lab, and we have been working on the consulting, onshore, offshore, or even tailings, of course, consulting and research and development projects. So I just listed our capability in terms of the advanced testing, but I think I should say for the audience here, we have a lab visit. Sorry, it's on Thursday, not Wednesday, but lab visit on day 3. So I would like to show you our lab, and we can discuss more in details that time. So since I have talked to you about this past and present, so I'd like to just quickly mention the future, because now I said we are in the temporary space, but then in the future, I suppose 3 years' time, 4 years' time, I don't know, but we will be back in the original place in a new lab facility at the moment. But I have nothing to say on this, so I just wanted to show this. Okay, coming back to the tailings. I think as Dominik mentioned, yes, we have been working on the lab testing services for the tailings dams. I just take one example here as a historical example. I think also Dominik mentioned already, so I don't really need to go through it, but the paper, I suppose, was coming from this project as well. But not only the triaxial test with the bend elements, we have been also working on the ring shear apparatus using a Bishop ring shear to look into, like, for example, residual strength and so on. So those has been a very great example for us to working on the tailings over the last 20 years. But then for the recent projects, we have been working together with Hydro, some people here, on the bauxite residue. So I'd like to start introducing some of the recent activities now. For example, first one here, bauxite residue has been increasing in amount, over the years, because we have to. That's coming from the production of the aluminum, and we have to dispose them. And the tailings dam has to be, of course, mechanically safe, but at the same time environmental friendly, so that we can use afterwards for closure. So what we have been doing as one of the recent activity, is that we are looking into soil improvement, at the same time the revegetation or vegetation of the plants on those soils. One master student came to us, worked with us, looking into the permeability aspect of the bauxite residue. So trying to improve the bauxite residue drainage capacity by introducing some of the other amendments. For example, in this case, he had bauxite residue, right-hand side bottom, you see 90%, let's say, fines content plus clay content of roughly 40%. But then he is trying to kind of correlate that conductivity measurements with the dry density. Then from there, we're trying to introduce, in this case, sand content, so that we can improve the consolidation parameters and the hydroconductivities of the materials. Of course, we could have gone further, looking at the different ratio of bauxite ratio, like 25%, 50%, those things. But at the same time, what we didn't do at that time, but we could have done was to look into different materials, locally available, for example. And at the same time, in the lab perspective, when we measure the permeability, quite often we kind of measure the permeability under saturated conditions. So that there is another research going on at the NGI looking into that permeability aspects, looking into, for example, unsaturated soil conditions. Under unsaturated conditions, what kind of permeability we can get as compared to the saturated conditions. That's more relevant, I suppose, to the tailings above the water table. At the same time, in this permeability project, I didn't prepare for this, but we also have been looking into the direction aspect, like a flow in a horizontal direction to the vertical direction and so on. So there are lots of research development happening right now at the NGI. So here's another example on the bauxite residue activity. This activity was to investigate the influence of soil amelioration of the bauxite residue on the vegetation growth and its consequence on the soil properties. So this was purely the experimental study to see if we can grow roots and plants. But the main part of this study was to use the X-ray image to understand how the root growth developed. So I'm presenting this as for the colleagues that they have been working on. For in this case, they have worked on a different mixture of the bauxite residue, for example, mixing with gypsum, for example, also adding the organic content or acai seed and so on, and trying to see how those mixtures can affect and which one can be beneficial for plant growth, for closure. So I just took one example here as a CT scan image. You can see in the CT scan, you can see the bauxite residue as a base in the gray here, but respect to that, you can see porosis or voids in black in this case, but at the same time, in a different color, you can see a little bit darker gray, like this to see that, oh, this can be the roots. So by using the X-ray processing tool, the methods, you can kind of evaluate how the roots can be was developed under the soil. If we don't have X-ray, we can of course see from the top, how the plants grown. But with the X-ray possibility, we can see how, how dense the roots can be and how deep the roots can be. As comparing to the first example in a bauxite residue 90 to 10 mixed with 10% gypsum, you can see the effect, as I see the organic matter as well as comparison here. So that study has concluded with the quantitative measures like this. After the 4 weeks of planting, you can see that most of the roots kind of developed in the mixture of 90% bauxite residue plus 10% gypsum. And that was having the high roots number and also the high root volume. But at the same time, in the other case, like a blue one, with mixing with acai seed 5%, you can also see some germinated, the seeds germinated, but then showing the deeper roots and so on. That study is very interesting to me, kind of a mix of possibility of environmental aspect. But then what could be a question is how about the long-term effects? You're talking about 2 weeks, 4 weeks, but how about long-term effects for the closure? But also, it could be interesting to continue this study to look into more mechanical behavior of soils with those roots. So then I'll move on to another topic, which is something more related to presentation previously, and there was a talk about the macro to the lab. So this is more like a mixture of macro and the lab. So I'd like to introduce this to you, the micromechanics on the tailings shearing behavior. So idea is to evaluate the triaxial shearing behaviors of tailings using the X-ray images. So as you can see here, the X-ray images, those four, or was three probably, was provided from UW on the tailings. You can see the particle size is totally different from coarse to fine, but at the same time, you can see how angular the particles can be. But the point is that using that X-ray CT scanner capability that we have in the lab to trying to understand much better in terms of strains, volume, void ratios, localization, failure development, failure plane development, by doing the triaxial test in the CT scanner. As compared to frozen technique, like end of test frozen technique, or the local AVDT technique that we have in the lab, I'm trying to see if we can improve further to understand a much better parameter sets for the CSL, critical state line. So let me just introduce quickly on this. We have a CT scanner in-house in the lab. That is a box or something like this. We have recently developed our triaxial setups to be used in the CT scanner. The sample size can be varied from the normal size to a much smaller scale. That was a collaboration with the Imperial College. But I want to mention also this, that we have been also working towards the rock mechanics part of it in this facility, so we have also capability to run like kind of a consolidation and scanning at the same time in the rock as well. So what happens in terms of triaxial tests? I just quickly want to mention. So this is the typical, let's say, this is an example from clay, but it's consolidated to certain consolidation stress, and we can do a compression loading, something like this. So what happens is that we can stop the shearing mode, and then we can scan so that you can see the whole picture of the sample. Otherwise, you don't really see it because it's covered by carbon fiber cells, so you don't really see it. But you can capture what's happening in the cell. And again, you stop and scan, you stop and scan, and you stop and scan, so that you can see how the sample has been moving or changing in shape. Another example here on tailings, relatively loose-ish, not too dense sample. You can see this is the example of the static liquefaction. When we start the test and the stop, you don't really see much, at the 1%, but then already stress strain curve shows really showing the peak and then already reduced in the strength. So trying to use this CT scanner and the image analysis tool to be able to track the volume and the area corrections better, and so that together with conventional method, we hope to kind of look into more details like a localized void ratio as well. Another example here I just like to mention, at the end of the test, quite often you may see something like this with failure plane. And in flight, while doing a test, of course, you can see very clearly. But on left-hand side, of course, you have to open the cell to see it. But then, when we use the image analysis tool, you can see at the very small strain level, like 0.5% to 1%, you can already see some kind of a band forming. So the image processing technique will allow us to kind of detect like a localization and a failure plane at a different level or different strain levels. And that will allow us really to look into more details on how we should interpret the test data. The idea we had, or we have, is that we want to look into the reconstitution method, like a different method. The example, yes, we have done mostly on moist stamping, but of course, we have to kind of go more detail into a different reconstitution method to create a different fabric. But then question remains, and we have discussed that in a discussion just now, and how representative is it to use the lab-created specimens to understand the in-situ behavior? That remains the questions, but if we can do something like this in a CT scanner, and if we have the samples hopefully available from the in-situ, we'll be able to kind of compare them in a microscope as well. So that's the kind of wish we have, and a potential research topic that we could have in the future. Also, I would like to mention one more. So as I said, we have different sample size available to do the triaxial test in the CT scanner. We have been working on one very, very tiny sample. This was 1 inch in diameter to look into grain-to-grain contact in a micro scale. I think I don't need to go into details because we have experts down here in Oivin working on this for his PhD. So, but still, we are trying to understand how the contacts are behaving, how the contacts are changing under the loading condition, in this case, cyclic loading condition, and trying to understand that in a micro scale and trying to understand together with the levels of DEM. We have tried that with the tailings materials, but then we have a limitation, of course, in terms of resolution of the CT scanner and also the particle size distribution that we have in the tailings, relatively quite small. But having said that, we should be able to kind of go forward with this technique if we have better resolution. If we have a smaller diameter, we should be able to kind of continue this work to understand the micro behavior of the tailings. The last slide for me here, because I thought of thinking about the future research on tailings, and I just like to mention this. So that is on a multi-directional loading behavior for slope stability. Often, when it comes to slope stability, we may do direct simple shear testing on the cyclic loading condition. When we look at the left-hand side figure, it's just an example. We try to look at the cyclic stress ratio versus N to come up with cyclic resistance ratio. But then, of course, at the slope level, with the slope sustained load, we may kind of add drain load in a monodirection, like here, to apply in one direction, and then we do a cyclic loading on the same direction. But now we have got a new capability in-house to be able to do multi-directional loading, something like this. So having a bias loading in one direction, let's say Y, but we can do a cyclic loading in a different direction to the bias loading. So it's just to give you the kind of idea. For example, this was done on quick clay, but it's similar, like slope stability issue. We are trying to understand if the direction of cyclic loading is affecting severely as compared to the monodirection cyclic loading. So we can, of course, go into more details on this, but I would like to just end my presentation with this figure. Of course, I'll be happy to talk about more on each testing device, but I will keep it that to day 3. And thank you very much for your attention.
Thank you so much, Yusuke, for the lovely presentation. Do we have any questions from the audience here? We give a minute for the audience online, maybe to post some questions, but before that, do we have any questions here? Yeah.
Hi, you mentioned sort of progressing the lab test work to compare against in-situ testing. Which in-situ testing do you think would complement the work you've been doing?
Sorry, so can you say that again?
Sorry. What in-situ, you mentioned that further research might include doing in-situ testing. Did you? Looking at in-situ data.
Okay. don't remember myself to talk about
sorry.
in-situ testing in my presentation, but I suppose in-situ testing can be done by CPT, of course. Is that what you were trying to ask?
Don't worry,
Yeah.
I think I
Yeah.
Sorry about that.
I had a question
Yes,
myself,
sure.
so I'm always okay. Yeah, sure.
Yes, very quickly. I was curious on the minimum particle size that can be resolved with X-ray micro-CT capabilities that you have.
Yes, that's the struggle. Yes, we have. For example, in this case, we have been working on the triaxial test in a small triaxial cell, 1 inch in diameter, 2 inch in height. And example here, we have, let's say, coarse sand in the picture here, having a 2 millimeter in diameter, a particle size. And we have been trying to use coarse, let's say, sand, but still less than 1 millimeter tailings on right-hand side top figure. But we are not able to see the particle sizes. So silt size, it's difficult. But still, you can kind of get the overall picture of how the volume, in terms of a whole volume, is changing.
Thank you. I'd love to follow up on that later.
Yeah, sure.
There is a question online. So have there been any efforts to characterize the permeability and isotropy of tailings in the lab?
We have not tried that on tailings yet. But what we have done so far was to two things, actually. One was on the intact samples, like a clarity samples, that where we have in-situ samples. We can kind of subsample in a horizontal direction and then put it on in a, let's say, flexible wall setup so that we can kind of measure. But another possibility now we have is we have made a cubical container with a filter stone on this axis so that we can introduce the flow while the preparation was done vertically so that we can measure the horizontal direction. We have just started, and this probability project is still ongoing. And on the tailings, yes, that's a potential, but we have not done in practice.
That could be the last question.
Hello. Looking at your CT scanner,
yes,
brings me back to the 1960s in Cambridge.
Yes.
Have you considered embedding lead shot, which is the technique they used back in 50 years ago to try and give markers which you could then follow and allow you could use silts or see the deformation pattern in silts?
Right, yes. I think that could be a very interesting topic. Matter of fact, in the tailing samples, sometimes we still see kind of minerals inside, and you can detect that in the sample. That's something actually we could kind of track, how that particle is moving, if we can see the particles. But we have not done, for example, we don't have the capacity of looking at the kind of PIV, basically the control system. We don't do that, but yeah, I'm aware of the technique.
Great. Oh, yes.
I just wanted to add to that you can also find like strain fields from like digital image correlation, even down to like clay size. So that's also an option.
Great. So that brings us to the end of the first session. So thank you all. And now we could all enjoy a cup of coffee. And for the people online, maybe you can grab a tea or a drink. And we see you back in another 25 minutes. Yeah. Hi, so welcome back after the coffee break. We can move on to our next session, which is about site characterization. So if we talk about tailings, it's very necessary how tailings behave on the field. No matter what we try to do with them in the laboratory, we need to understand how they behave on the field. So now we have two experts with us. The first one would be Simon Dickinson from the BGC, and he's a principal geotechnical engineer with 20+ years of experience in tailings dam projects, focusing on design, site investigations, and advanced laboratory testing. Please note that the two speakers of this session would first like to complete their presentations, and then the floor would be open for questions. This is to kind of have more engaging discussions following the two presentations. The floor is yours. Yes.
Thank you, Sparsha. Yeah, I actually feel very fortunate in the slot that I'm in, because I think my talk follows pretty naturally from the two terrific talks we heard this morning with more of a research focus, and in fact ending with a statement or question about can we rely on reconstituted samples in order to inform us on in situ behavior, especially in light of the fabric effect which is plaguing kind of all of our lives, whether it be in the research field or in the applied field. So my background is as a practicing tailings engineer, splitting my time basically between internal tailings projects for which we're engineers of record, and also various review assignments, ITRBs for international mining companies. And so what I'm going to talk about today is a field case which actually tackles some of these issues that have been raised this morning around reliability of these methods in light of things like in situ fabric. And one of the units that we deal with a lot in Canada at a number of different mining sites relates to glaciolacustrine deposits that are laminated or layered quite often at a very finite scale, very small scale, which makes it very challenging at times to, for example, pull them apart and tackle each constituent separately, as we might do in a tailings deposit. And so the focus of this talk is actually around the characterization of microlaminated or laminated glaciolacustrine deposits that we encounter in the Canadian Shield throughout Canada and northern Canada. And I'm going to start with a focusing statement, because what we're actually going to talk about, or I'm going to talk about here, is not characterization of tailings. However, it is incredibly relevant to tailings dam design and construction. And so these are soils that exist within the foundation of these dams. And I think all of us are becoming quite comfortable at characterizing tailings. There's certainly been an awful lot of research and practice put forward in that world. But we're kind of catching up with applying similar methodologies to characterizing silts, sands that reside in a loose state within the dam foundations. And I'm starting with a focusing statement here that many liquefaction failures have been attributed to the foundation materials. And so it's critically important to understand what we are building on. And here's just a very brief summary of some of the more recognized cases. A really quick Canadian geology lesson. This is the Laurentide ice sheet during the Wisconsin at its maximum extent about 18,000 years ago, where the isolines or contours represent thousands of years before present, immediately before the ice sheet started to retreat. And as it retreated north towards Hudson Bay, there was a massive glacial lake that occurred across the Canadian Shield, referred to as Lake Agassiz. And it was into this lake where there was a tremendous amount of sediment deposited from the melting ice. And that ranged, depending on the proximity of the ice sheet to the lake, anywhere from thick, many meter scale clay deposits in the deeper water environment to near shore, more of a silt and sand ice contact deposits. And quite often these units are stratified, layered, either meters thick, centimeters thick, and down to micrometer thick layering depending on the season, depending on the energy at deposition, proximity to the ice, etc. And so the environment that we're particularly interested here, where we end up with these very loose silts and sands, is quite proximal to the ice sheet during the breaking up of the ice. And what you can see here is just representation of that ice sheet melting. And what we're looking at is deposition or deposits that were dumped into the lake, quite handy to the ice sheet. The case study that I'm going to talk about is one that I'm not disclosing the site, but at the same time, the actual location of the site doesn't matter. It's quite representative of a variety of sites in northern Canada within that Lake Agassiz depositional environment. But this represents the stratigraphy of this particular site. As you can see, a peat or organics layer at the top into a glaciolacustran unit that has various different facies within, ranging from sandy silt to a little bit of clay with some silt and sand, and back into silt, which may be laminated or homogeneous. And then there is a till over bedrock. But we're going to focus on the red box, which is that glaciolacustran unit, which at this site and at many of these sites is often quite loose, which raises the potential for it to be liquefiable. And so I'm using this term microlaminated just to give a quick overview of what I mean by that and why it's particularly challenged. And this speaks directly back to this fabric question. So this is all within the same unit. It's actually all within the same borehole, to be honest. But on the left, we have a varved sequence. This is a little bit more typical of what we would often imagine even within tailings, where we have slimes and sands, for example. And it gives you a chance to pull those apart and to tackle each of these materials separately, to characterize them in terms of their critical state and constitutive model parameters, NORSAM parameters, and deal with them separately. But what are particularly challenging are these ones in the middle, which is what I'm referring to as microlaminated, where they have a fabric that is quite obviously layered, but it's not practical to pull it apart and to try and tackle each of these layers separately. So it has to be dealt with as a continuum. And then at the far extreme on the right is the other extreme, which is, in some cases, these are actually quite homogeneous materials, and then that becomes quite easy to characterize because, again, we're back to a uniform material that can be quite well replicated in the laboratory. And so on this project, I'm going to start, or I'll just walk you through the journey that we went on with this material to characterize it and to apply some of these techniques that have been discussed this morning. So what you can see in gray is the range of gradations from a representative number of samples within this material. We then identified two what we referred to as representative material types that we blended together in order to make bulk samples for the purposes of reconstituting representative materials to then go on to carry out an advanced testing program for characterization of critical state lines. So for the purposes of this, we're going to refer to those as GLU1 and GLU2, glaciolacustran unit 1 and 2, where 1 is a non-plastic, pure silt material, and the difference with 2 is 2 has a little bit of plasticity, not much, a PI in the kind of 4 to 7 range. So it's in that CL/ML range, but it's a little bit more plastic. And so from that point, then we went down the road of preparing reconstituted samples. We used moist tamping to prepare these samples and came up with a critical state line. This is GLU1, and did some dense tests for the purposes of establishing NORSAN constitutive dilatancy parameters. So this is a look at GLU1. This is GLU2. Again, nothing really out of the ordinary. Quite good repeatability, and felt pretty good about where we landed with our reconstitution. And here's just a look at these two together. And what you can see, quite low CSLs in the void ratio space. That's just owing to the particular nature of the material, having quite a high degree of packing. And you can see that the slopes are fairly flat, not uncommon for silt, quite low compressibility, which is giving it quite a flat critical state line, which I think for those of you that can imagine, meaning that there's quite the potential for brittle behavior. And a little bit steeper on GLU2, just owing to that clay mineralogy that just gives it a little bit more compressibility. And it was at this point, well, I guess not to jump too far ahead. So then, from this point, we then went through the Norsand calibration procedure. These represent the fits, the various fits of the various Norsand parameters for GLU1. A couple of things that are interesting to point out here. You'll see very high hardening coefficients relative to literature, certainly when compared to tailings, and a very low N value. Now, low N, because of the nature of the equation, really what that means is that the steepness of that curve is approaching a slope of unity. So there's nothing particularly magical about an N of 0, other than actually it's the fundamental assumption in cam clay. So by virtue of coincidence, this material is actually a material that could be quite well captured with a cam clay model or modified cam clay. I just point those out for discussion again, and it's something that we have seen with these very dilatant, very stiff glacial lacustrine materials that are residing at very low void ratios. Here's just an example of some typical fits for our Norsand calibration for GLU1. We went through the same process for GLU2, and here's a case actually where N actually was negative, again indicating that this line in stress ratio versus d min space actually reached a slope steeper than unity, again attributed to the very stiff and dilatant nature of these silts. And again, walking through some of the fits for our various GLU2 material. And this is where the story gets quite interesting, because we had the idea at that time, this is a project that we had worked on for a number of years, is, well, let's go back in our database of all the triaxial tests that we have carried out at this site previously on intact or in situ specimens. And let's see how they compared to these new representative reconstituted critical state lines. And that's what's showing up here. And what you can see very quickly is they really didn't agree very well at all. And in fact, it looks, we have states that are plotting well above the critical state for either material that were actually highly dilatant, diving up to very high confining stresses, which really would suggest that these critical state lines don't represent those materials at all. And so this got us asking, well, okay, what's going on? And so having run out of GLU1 and GLU2 materials, that's something that we're always faced with, is that there's only so many samples. That's okay. We found another material that was quite similar from a slightly different area. And we said, well, let's start doing some experiments on that material to see if we can understand what's going on. And so we coined this material GLU3, and that's what's referred to in the black line. So as you can see, very similar to gradationally to the other two, and very, very, very similar to GLU1 in terms of its mineralogy. So again, completely non-plastic, no clay content, so much more similar to GLU1 than to GLU2. And we took that material and we started by going down the same road. So we made reconstituted samples to establish its reconstituted critical state line as a starting point. And here's what we discovered now. So despite having very similar gradation to the other two, we've discovered yet another critical state line within this deposit where all three of these were prepared in the same way. These are all representing reconstituted critical states. And so what we've learned just at this point, without going any farther, is that there is obviously a variety of critical state lines within this deposit, owing to changes in the relative gradation, the degree of packing, and in some cases the mineralogy, especially between GLU 1 and 2 and between 2 and 3. But the other thing that you'll notice is that the slope of the critical state for 1 and 3 are identical. And we thought that was quite compelling because we know that the slope should be controlled largely by the mineralogy. And where GLU 1 and 3 were very similar in terms of their composition, and the only real difference being some subtle differences in gradation, that kind of made sense. So the next thing we did here was we said, okay, we have more of GLU 3. We have some intact samples of GLU 3. So we took an intact sample out of a Shelby tube, and we ran a test. And this is what it did. So this is our starting point, very handy to actually to the critical state line for that material. And lo and behold, once again, it dilated quite heavily away from the critical state line. So now we have direct evidence that the fabric effect here is very much influencing the position of the critical state line. So the next thing that we did here to further investigate it is we took the identical material that had been tested here after the test, and we actually just remixed it back up. So we took the in situ test, we smashed it up, and we reconstituted the sample, and we prepared it, or attempted to prepare it, to the same starting void ratio. We missed a little bit, it was a little bit higher. But now, what we see is a behavior that's very different. It's now contracting, and it's actually contracting back to the reconstituted critical state line. So in comparing these two tests directly, we now have direct evidence that the fabric effect in these microlaminated deposits is controlling the position of the critical state line. But we also have indication, because the mineralogy is the same, that the slopes of these critical state lines should be fairly similar, all things being equal. And so we made an assumption, just for the purposes of this exercise. And we said, okay, the position of the critical state line is moving, but the slope is remaining unchanged. And so what we did is we developed what we're referring to as an interpreted intact critical state line. All we did was take the critical state line for GLU 3, and we shifted it up so that it matched the endpoint of test CIU 311, which we thought was a fairly reasonable thing to do. But the interesting thing about it is we also have the ability to check that assumption within our Norsand calibration to see if this is reasonable. In other words, is it reasonable to hold the slope and the other Norsand parameters constant or consistent and only shift the position of the CSL? And we do that simply by running Norsand again with the new interpreted CSL, but leaving everything else the same, and seeing how well it simulates that in situ test. And what we found in doing that, so this is the only thing we did here, was shift the CSL up in elevation on E log P space. And we actually see we get a really good fit. The reason that this is really important is because, and I'm going to get in it, when we get into the next focus of this talk, which is going to be the so what, or the what does this mean in terms of our ability to determine in situ state parameters. The reason this is important is because if the only thing changing is the position of the critical state line and not its fundamental slope or stress dilatancy parameters, then our cavity expansion process, which we use to back out in situ state, is not sensitive to the vertical position of the CSL. So gamma does not come into it. So the widget the cavity expansion widget operates from a state perspective relative to the CSL, but as if it is not sensitive to the elevation of the CSL. And so what does that mean? Well, if we run, I'm gonna move on now and start looking at what this means in terms of our in situ determination of state parameters and some of the revelations that came to light. So what you're seeing here is a cone trace directly adjacent actually to where sample GLU3 came from. So this was a paired borehole where we pushed the cone directly adjacent, went sampling, and that's where that in situ test CIU 311 came from at a depth of about 15 meters. And what I'm starting with here are the screening methods, so Pluis and Robertson, and you can see inferred state parameter on the right versus depth. And in red, this is our typical minus 0.05 state cutoff for where we're concerned about liquefaction potential. Using the cavity expansion and Norsand and Jefferies and Bean approach of 2016, this is where our state parameter profile plots on that plot. And so this is using effectively that critical state line slope for GLU1 in the case of drained conditions, as indicated by the BQ. So essentially when there's no pore pressure response, we assign parameters for GLU1, and if there is a pore pressure response, we use the GLU2. But really of note, what we really want to talk about is happening up here at the sample depth where GLU1 or drain conditions are applying. So what we then started to do is, well, we weren't really sure about this assumption of, do the other Norsand parameters change? And we went through a series of sensitivity analyses to test that assumption. And what you can see here is just the range of sensitivities that we did by monkeying with the chi value and the hardening parameters. And what we discovered for this material is that the actual cavity expansion was not particularly sensitive to any of these four parameters, which again gives us a bit of comfort that making our assumption of shifting the critical state line but not changing anything else was a reasonable thing to do in this case. Where it did become sensitive is when we started changing the slope of the critical state line. And I don't think that revelation is really new to anybody. I think we can all recognize that the slope of the critical state line is probably the most dominant control when it comes to the cavity expansion estimation of state. And the last few slides, and I think really kind of drive home what we felt was a pretty important point, was that we have a critical state line that we're referring to as the interpreted critical state line. And by virtue of placing that up here, what we're able to actually do is estimate what we think was the initial state parameter of that sample prior to testing in terms of that intact sample. And if you do that or calculate it, what you find is that state parameter was at about minus 0.04. When we go and look at what the cavity expansion process gave us, the widget, what you'll see, this is where minus 0.04 plots. And what that tells us then, at least in this particular case, is that the cavity expansion process almost perfectly replicated what the laboratory data was telling us with that shift. And again, the reason for it is the reason I alluded to earlier, which is that the cavity expansion process is not sensitive to the position. It's only sensitive effectively to the slope of the critical state line. And we have every reason to believe that actually the slope through the reconstitution process doesn't change. Where you could get into trouble, and this is a cautionary note, is if we were to use a direct measurement of void ratio, which we often do using, for example, in situ water content as being an indicator with an assumption of 100% saturation, which would calculate a void ratio directly. What you would find is that you would greatly overpredict the in situ state. And that is for the reason noted here, that in reconstituting, your critical state line is dropping. And so it's a caution that we have to be very careful with these materials if we are using direct measurements of void ratio or direct estimates of void ratio and trying to couple those with what we're getting out of, for example, the cavity expansion process that is relying on state or effectively relative distance to the critical state line. Because as that critical state line moves around, you know, the state isn't changing, but if we're relying on an anchor point in void ratio space, we're going to potentially get the wrong answer. And in fact, we have many cases in our files where we tend to find getting very good matches like this, as I'm demonstrating, between interpreted CSLs or interpreted state parameters, but we don't always get good matches, especially in these natural silts, between our in situ measured water contents. And I firmly think that this is the reason why. So to finish up, I've got 2 minutes here. I've pulled out 4 conclusions from this as discussion points, just in the hopes of generating some debate. One is that the CSL varies in altitude within a microlaminated glaciolacustran deposit. So we need to think of these deposits as having an infinite number of critical state lines that are varying just by minor changes in the relative gradation. But the slope of the critical state lines appear to be similar for similar mineralogy, and GLU 1 and 3 being a very good indication with identical slopes, even though they're quite offset from each other in altitude. The altitude, the gamma coefficient in our critical state speak of the microlaminated soils is not unique when comparing in situ versus reconstituted materials. So the position of that critical state line is going to change. This is not a new revelation, and in fact, I do want to give a plug to my friend Dave Reed at UWA, who published a paper last year, and it's in my reference list, where he really attacked this issue by looking at tailings and this layering effect, and actually demonstrated in a similar way that by mixing versus reconstituted, you get this shift of critical state line. So this is not a new revelation, but it is one that is critical to the fundamental discussion here. The lambda, however, we think will be the same. Again, if it's, you know, provided the mineralogy is similar. And provided the slope is unchanged, then the fabric effect associated with the microlaminated deposits may not adversely influence our ability to interpret the in situ state. And again, this is circling back to the fundamental question of, does it matter? What does this fabric effect do? In our case, in this particular case, what we were able to show is that, in fact, using a reconstituted, moist-tamped material to replicate a very structured, fabric-rich material, we were still able to get the right answer using the approach that Mike and co have laid out for us. And a final caution that we have to be careful, however, because you will end up with the wrong conclusion if you start mixing methods and you start using, you know, reconstituted critical state lines and then start plotting in situ void ratios directly, because again, those are not compatible, and you can end up, I think typically you'll end up with a conservative answer, which is probably good as a geotechnical engineer, not necessarily good as an owner, because the implications of it can be extremely severe economically. Again, I have a reference list that is provided in the presentation. And that's it. And again, I guess we're holding questions until Mike has done his, but I'm going to get out of the way. So yeah, I appreciate it. Thank you.
More time, we move on to Mike Jefferies. He asked me not to give any long introductions, so he's one of the, I could call one of the fathers of the Northsand model and the man who wrote the book that we have been referring to right from the beginning. So the floor is yours.
Thank you. I would hesitate to call what I'm about to show you as a presentation. This is a workshop, so I've not come here to tell you about new findings or to show you some derivations or something like that. Rather, I've come with two complaints. I want to raise two topics where I think we as a profession aren't facing up to things. And I shall now put on my Kevlar vest. Back up. This talk is about the CPT. And with the CPT, we measure, I've said four things. We get QT, FS, and U2 as a data stream. And generally, we'll use a seismic cone as well. So we'll have a Gmax profile as well. And that's our input data set. What we want to get out of that as engineers is the state parameter. I'm not going to address stochastic variability of the state parameter because there are two issues. What's the state parameter because the material changes, and within a constant stratum, you can also have stochastic variation to void ratio, which gives you stochastic variation. So within my time limit, I can't do stochastic variability, but I want to do material effects. Now, the basic problem is this. What I'll show you on the screen here, the vertical axis is just normalized tip resistance, and that's the state parameter across the bottom. And the results on the screen is, I don't know, 8 calibration chamber tests. And each of those calibration chamber tests, we've fitted what we've measured and put a trend line through it, and that's what you see in color. And the problem is this. If you go to a typical tailings beach above water, maybe a little bit of subaqueous beach, whatever, you'll get tip resistances will plot somewhere like the purple line I'm showing you there. It's not an atypical line for those of you who test tailings. And the problem is this. If you say, my tailings corresponds to the green calibration, you will infer a state parameter of about minus 0.08. You will be a very happy bunny, and so will your client. This is dilatant and safe. Conversely, if the brown calibration applies, you'll have a state parameter slightly positive. Contractive, statically liquefiable, you run a dozer over it. Huge remedial works are required. And your decisions as an engineer does not depend on your input CPT data, which is purple. It depends on your choice of calibration. And this calibration factor, for pretty much all the tailings jobs I've seen, is the essence of the engineering. But what you see is people faff around with the CPT. But you've got to say, okay, what am I going to do with the data? Now, we've known about this issue as a profession from at least the mid-80s. And it's usually called an effect of compressibility on the penetration resistance. Well, there's more to it than compressibility, but just hold that idea in your head for the moment. Because compressibility equals lambda, which is what previous presenters have been talking about. We have, when you're coming to calibrate your CPT or choose which calibration to use, on the table today, we have 4 methods. You can do a campaign of calibration chamber tests, and that's the photo you see on the right. And in essence, a calibration chamber is a very large triaxial test. That's one of my former colleagues doing the test there. And what you have, if I can get the, whoops, sorry, press the wrong button. Let's get the light up. That is a standard CPT, standard 10 centimeter square CPT. And we have a giant triaxial test. There's 2 tons of sand in there, prepared to a known density, and we can independently stress it horizontally and vertically, or radially and vertically. We just push the CPT into it, and we can develop a mapping between tip resistance, state parameter or void ratio, and confining stress. But it takes 2 tons. and expensive. I have only seen chamber tests done on 2 commercial projects. One was paid for by the oil industry in Canada, and the other was Chet Blackcock Airport in Hong Kong. This is generally not used in practice. So our second or third approaches are we can actually say, what is this compressibility of which we speak? How does it affect what other soil properties affect our CPT calibration? The traditional way of looking at that has been non-associated Moore Coulomb. And there's a very nice paper by John Carter in 1986 using that technique. Or we can put in fancy models. The one done with Dawn and myself, we use Norsand, but there are other ones as well. But we can use cavity expansion methods. We're seeing now people getting very keen on the material point method, which is a further step forward in finite element analysis. And it's not new to you, the CPT with finite elements. The first guy, I believe, to try it was Steve Wilson at Manchester back in about 1985. Professor Hicks can maybe update me on that one. And then Van den Berg at Delft did a very nice thesis on it, again, trying to look at the CPT with FE. But it's a very difficult thing to do with finite element method. So it was not commonly used. But the essence there is we're using soil properties and trying to understand. And the third thing that's come into play recently is something called mini-cal. And mini-cal is simply we take that test there, we do the same thing in principle, but we massively shrink it. So why it's called mini-cal. So now all of a sudden our calibration chamber is this big, and we're using a cone that's like a knitting needle. And we're saying, okay, we can sort things out. So with that as way of introduction, most practical projects, we're not going to do large-scale calibration testing. So we're going to want to use soil properties. So what soil properties matter, and how does it come together? The basic idea in all modern constitutive models traces back to Don Taylor and Alan Bishop, who said that soil strength comprises 2 components. We're not doing the Terzaghi model. Well, they say if you take a simple shear device, a direct shear device, which is what you see down here, shear box, and if you take a dense sample and you shear it, the platen will rise. If the platen is rising, it's doing work. What these guys said, and this dates back to 1950, is that you have to allow for this dilation effect on soil strength. It's what originally was called the friction plus interlocking model. And what I'm showing you on the screen is data that fits their idealization. I've got silts, sands, and clays on that plot. And the same equation works. Properties vary, but this stress latency model is truth. There's no such thing as cohesion in a particulate material. And that underlies everything. But of course, the question is, on the bottom, we have dilatancy. Well, how does this dilatancy happen? Where's the magic? Why does this number occur? Well, the answer is very simple. Not simple, actually. Critical state theory is based on the canonical characterization produced by Casagrande. He never did it, but you can apply maths to that characterization. And if you apply maths, you can come up with the idea, or the maths say the basic kernel of Casagrande's idea, as distortion strain goes to infinity, the soil moves to its critical state. Well, that's mathematically more elegant if we say we have an offset from the critical state. That offset goes to 0. And the offset is obviously the state parameter. So we can do some math around that equation. And that math leads you to this equation. The limiting dilatancy, which is what d min is, will be linearly related to the state parameter. And we find that is true, again, it doesn't matter if you're silt, sands, or clays. Now, I should say here, based on Simon's presentation, I'm being a little quick with the math. Because when you do the math properly, there should be a 1 plus e term underneath that. There isn't actually an effective void ratio. And this is one of my regrets, is that we rushed to plot data as consulting engineers and then did the math later. If I'd done the math properly beforehand, that equation would read chi over 1 plus e. So when we go to these denser soils, and conversely, when we go to very loose soils, we shouldn't be surprised that the chi value is not quite what we expect. For speed, I'm going to skip over that slide. Now let me talk about cavity expansion solutions. The data set on the screen you see here, which I've, whoops, don't want to highlight, go back a bit. No, sorry, I'm losing control here. This top data set with this top bracket, that is the comprehensive set of chamber tests done by the Italians and Ticino Sand. Nobody has done a comprehensive program of those guys. And what I'm plotting here is their normalized tip resistance versus the state parameter, which previously I've just shown you as a trend line. This is the individual results. And each one of those dots is a run of 2 tons of sand being tested. So there's a lot of tons of sand being tested. The reason I have flagged the 2 tests which are highlighted in purple arrows, those tests are reported to have the same initial void ratio and the same initial confining stress to 3 significant figures identical. But the reported tip resistance varies by a factor of 2. Now, you shouldn't throw bricks at them because it's difficult to make 2 tons of sand to a specific void ratio, right? And to measure that. And the second thing is when you put a cone through a chamber test, it's not a straight line. It wiggles all over the place. So you're going to have to make some judgments of what is representative. And what I say is a good chunk of the scatter is actually experimental uncertainty. But don't throw bricks at them. This is a result of doing careful testing, but you're dealing with 2 tons. Now, what we've done on the bottom dots, or the ones which are light-colored, we've taken a finite element cavity expansion solution using Norsand, large displacement, yap-a-dee-yap, and we have taken every E0, P0 pair from the chamber test, and we plug that in and run a cavity expansion solution. And the reason we have some scatter, it's not scatter at all, it's actually systematic. Oh, come on. Where's my... Okay, I've lost my markers. I'll tell you what's going to happen. Step upstream. That scatter is caused by variation in Gmax. It's not scatter, it's systematic behavior. So we need to take Gmax out of the equation. And the question you've got to ask is, why is the cavity expansion solution not perfect? Why is it significantly different? So we have to use a scaling factor, what we call CQ, to relate cavity expansion to actual CPT. So why are they not the same? Well, this slide shows you what the difference. On my left here, I've got a CPT, and it says CPT on it. And the pink is what we've got in the cavity expansion solution. The cavity expansion solution has no concept of vertical, whatever. We've reduced everything to just radial. And we say the limit pressure is related to the load on the tip. But notice we have friction on the side of the cone. We know we have friction, we measure it. Now you say, oh, okay, Mike, friction's small. 1% maybe, 2% maybe 0.5%. But what you're missing is, number one, the friction sleeve is 15 times the area of the tip. Second, that friction doesn't stop at the friction sleeve, it goes all the way up the cone rods. So we're actually feeding load into the tip, or around the tip. And you can see from my black arrow, that's going to appear, in effect, as an additional confining stress. And further, it's not small. If you actually go and plot your measured friction, which is what I'm doing here, and normalize it by the vertical effective stress at the depth of the friction sleeve, you get a plot that looks like this. This is some loose sand fill, some denser sand fill. And you'll notice these values are way above a sand-steel friction ratio. But the reason is because you've got a lot of dilation. And the dilation is massively amplifying the horizontal stress, which is how we mobilize it. But it's this missing stress, which is why we have to scale cavity expansion solutions. And this is their limitation. It all comes down to how we scale. Now, the first thing I'll show this one quickly. Mason Gafghazi, who's now a prof at U of T, for his doctoral thesis, he went through more or less every of one of the world's calibration chamber tests, applied the cavity expansion thing, and demonstrated the CQ factor did not vary from one sand to another. An important step. When we came to tailing silts, which is what you're all interested in, it's generally an undrained CPT rather than a drained CPT. So what we said was, okay, cavity expansion still applies, and undrained is just a boundary condition. Nothing in the mathematics of North sand or the finite element method changes. All we change is whether the pore water is allowed to move or not. The mechanics are identical. The math is the same. When you do cavity expansion, in fact, you compute the U1 pore pressure on the middle of the tip. We actually measure on the cone shoulder as our standard. We've now updated the process, but it's not in the paper, to actually compute the U2 pore pressure. And what you get when you run this calibration, we have to do two things. First off, we now have to put the measured pore pressure from the CPT into the vertical axis. So instead of using just Q, it now becomes Q times 1 minus BQ plus 1, which looks terribly inelegant, but it's the same thing as tip resistance minus U2 over sigma V minus U naught. And you get lovely trend lines. But also, you can predict the BQ value, which is what we've done down here. So we actually have two methods now of using this thing. This now, let's look at how it all works in practice. This is Cadia, their failure. And on the left-hand shot is an aerial photo of the slump. In purple is a CPT. And that CPT, bless them, was done about 1 year before the failure occurred. It's not quite perfectly on axis, but damn it, this is as good as you ever get to getting a CPT in material that's subsequently liquefied. On the right-hand side is the results of taking that CPT, which we were given as the RTIB as an Excel file, and we applied the North sand method. We got some tailings, got the properties and so forth, and ran North sand, the calibration procedure, and this is what we computed. The green dots are when we use the tip resistance calibration to get to the state parameter. The blue dots are when we use the pore pressure directly. I said we had two methods. What we see here, they're not perfectly on top of each other, but it's damn good. So we've got a lot of confidence in that. The gray lines by background are the Pluis method, which I'll come to in a moment. So we said that we were quite pleased with this. And then what really made my day was we discovered this memo by the engineer of record. And bless them, what this engineer of record had done, they had gone out. Sorry, it's a bit grainy. It looked a lot better on my computer. They had done some very fancy piston sampling. Piston sampling with a compressed air cutter at the bottom. You know, about the highest quality sampling they could conceive of. And the people who did it are very proud of the testing. And they'd done this on the borehole right next to the CPT. And bless them, they'd actually documented the void ratios. And what we have down here is the void ratio, and these are the samples they got with their various piston samples, and those were the initial void ratios. And down here is the as-tested void ratio. So the comment I raised, well, we had discussion earlier saying, can you get a perfect sample of silts? The answer is absolutely not. You can see a pretty massive void ratio change from in situ to as tested. And it's not unreasonable, because you've taken the sample, you've taken the stress off it, you put it in a pickup, you maybe have packed some rubber foam around it, you maybe tilted it, you then put it in an extrusion rig, pushed it out, trimmed it, twisted it, reconsolidated it. Are you surprised it's changed void ratio? You've got to remember, silts behave more like sand. They're fine sand. They don't stick together. And you get massive densification. And the problem was, if you test down at this void ratio, you'll say the stuff is dilatant, not liquefiable. In situ, it's as liquefiable as hell. Okay? But anyway, I digress, because I say we had tested the sands, or tailings, and we had a range of tailings at Cadia, but we said there's a predominant gradation. We called it TC1. And there was seen to be some sandier lenses, which we called TS1. And we determined the CSL for those. Now, we don't know what was in those tubes. You've got to remember this is in the middle of a lawsuit. We're an ITRB. We're not allowed to talk to the engineer of record. All we have is what we can discover. We did not discover a testing report from the field activity. We didn't discover a lab extrusion report. So we don't know what was in the tubes. So we said, okay, if the tubes are full of the sandier stuff, which is the brown line, we would compute the in-situ state parameter, which is the brown dots. If the tubes are full of the predominant material, we get the blue dots. And they straddle what we got. So we were pretty pleased with this. And then last Christmas, Dave Reed spoiled my day. What Dave did, Juan and Andy and Dave, they put out a paper saying, well, we've got some platinum tailings, we've got some gold tailings, and we've tested them in a chamber. I'll come to you with detail of the chamber in a second. And what we've measured is these trend lines. If we run the cavity expansion approach, we get down here. So they said things aren't really quite good enough. And I didn't believe we could have this workshop without Dave Reed. So the smiling chap on the right is Dave, for those of you who don't know him. And Juan is the guy on the left. And that's their CPT chamber. You can see the size of it. This is one of the first one of the mini cals. And you can see the size of the CPT we're using. So what we have changed here, we're changing material type, we're changing our test procedures. And then what really shocked me when I came to put this talk together was I found this. There's a manufacturer now making this equipment and selling it commercially and saying it is fit for use, engineering use. And the problem I've got, and perhaps one of you can raise a point in discussion or point me to a paper I haven't seen, but when I go back to the 80s, and I'm an 80s bunny, we did a lot of work as a profession with large calibration chambers. Various organizations contributed to the debate. We discussed chamber size effects and various other factors. We even had a conference on calibration chamber tests. I do not see any of these mini-cal people demonstrating backward compatibility to the large chamber database. And we've changed a number of things here. You know, I don't know whether the boundaries are sufficiently large, whether a small CPT has a grain size effect. But we are changing our procedures as a profession, and we've not done our homework. That's why I'm wearing Kevlar vest, by the way, so don't throw bricks. And this bothers me. So when I said I came not with a presentation facts, but an issue, I think this is an issue we need to worry about. So that's small chambers, or mini-cals. People are now getting very excited with the finite element method, or more particularly, the material point method. And people seem to be having more success in doing or getting a CPT to work computationally with the NPM than they have done with traditional large strained finite elements. This is also from last December, picked up from Geotechnical letters. The left-hand plot shows what they put on, and I put a green line through, is what they've got with the material point method. The blue line I've highlighted is their experimental data. And even when they say this is good fit, if you look, there are two things going on here. They've got a very compressed scale, so it's making it look better than it really is, and the gradient is not the same. If I translate that green line over to Ticino sand, which is again a not dissimilar quartz sand, it's hellishly different. So what I say is material point method is definitely a step forward, but again, as a profession, we shouldn't say this is replacing, at the moment, our calibrated cavity expansion methods. It's promising, and I think it's, but there are two things on the table now we've got to sort out as a profession. And I should say, since this is workshop is sponsored by NGI, NGI is one of the outfits did large calibration chamber testing in mid-80s, 1986, on Hoxsund. So my challenge to you NGI people here is you should get a mini-cal and test Hoxsund in it and see if it duplicates your 1986 paper. My challenge to you. Moving on to my second topic, and this is back to now what we do in the real tailings example. Here we've got a CPT in tailings. And what I've highlighted on the right-hand side in blue is, oops, I don't want that. Let's go with this a second. There's my speak. That's our friction ratio, and that's our BQ. And based on that, and that's our soil behavior type. And you can, I don't know whether you like to run with BQ or you like to run with friction ratio or you like the soil behavior type, but you've clearly got pretty uniform material down here that in principle can be piston sampled. I would actually say you've got two materials. I think that one's slightly different from this one. But in principle, you can piston sample that to determine the mechanical properties to then either put into NPM or you can do a calibrated widget. And in principle, you could actually get enough sample to test in the mini-cal. But what on earth are you going to do up there? Look how the stuff is changing. And it's changing at the scale of, 100 millimeters, 200 millimeters. You can't test this stuff or sample this stuff with a piston sample and get reasonable samples. What are you going to do? And you've seen on Simon's presentation, it can get more complicated than that. So what are we going to do as engineers? How are we going to cope with point-to-point material variability? Well, the idea we had back, again, it's the mid-80s, I'm a 1980s bunny, we said if you took a soil behavior chart of this type, where we've introduced the pore pressure into the chart, so we're plotting Q times 1 minus BQ plus 1 versus friction ratio. The plastic hardening, any constitutive model which is related, uses a concept of a critical state locus. The plastic hardening modules they will use will be roughly related to 1 over lambda minus kappa, which is actually the Cam Clay thing. But if you're looking into a critical state line, your plastic hardening will come down something approximating that. And if we look at a material behavior chart like this, top left will have lambda values, or lambda 10 values, 0.05, and M of 1.3. Bottom right, and that's typical clean quartz sand. Bottom right on the diagram, M's maybe dropping down to 0.9, and the compressibility has gone through the roof. Maybe lambda 10 is now 0.3, could be 0.4, could even be higher. So what we have in a soil behavior type diagram is that soil properties systematically vary top left to bottom right. But what we also know is that there is an effect of the state parameter and also of a consolidation ratio. So for any given soil, it gets more resistant the denser it gets and the stiffer it gets. So all we have is an orthogonal map for the state parameter and OCR. So you can, in principle, take a soil behavior type diagram and you say, okay, this gives me a basis for looking at the CPT on a data point by data point by data point basis. Because to do that, what you have to do is map soil properties to your soil behavior type. So how do we do that? Well, we actually looked at using soil behavior type, but what we found worked the best, and this is what's in the Pluis method, we found lambda, which again other speakers talked to, was basically friction ratio in percent divided by 10. A very easy to remember equation. Subsequently, and of course, when you first do these things line up and you're very excited and you think it's very good. Subsequently, we discovered, in fact, the bandwidth is rather larger than we thought, and Dave Reed has added some more data points, but we know that there is a bandwidth associated with the Pluis method, and that's the bandwidth is what limits its precision. Going forward, if I take that CPT I've just shown you and apply the Pluis method to it, that's the kind of state parameter thing you get. It now is nicely picking up the effect of changing soil properties on the fly. And this is massively used in commercial practice today. Because, look at it. There's no real input. You've got the CPT. The CPT is measured friction ratio. You know lambda. You can make a guess at M, because if you look at the soil particles or if you've got some history in the area, you can guess what M is, or S, guess. Let's use the engine term. You can make a judgment on what M is. And away you go. See why it's so popular. What people forget, though, is when we proposed this method, we said it was, first of all, we called it a screening method, because there's actually more involved than just lambda. And you also got to bear in mind it's the knowledge base. I put 1990 on it. It's really a knowledge base of about 1986. And it does work beautifully much of the time. It works far better than has any scientific right to work. But the problem is there are no indicators where it's not working. There is no condition anybody's revealed to me that says, okay, this particular parameter or something will tell me, no, Pluis has gone out of calibration. So it needs a site-specific check if you're using it. But also, I think it needs improvement. So this is where I'm going to finish up. This is where the folks at University of Western Australia are going. They're saying, okay, we can start using these calibrated cavity expansion methods. We can use the updated view on what the lambdas are. We can use Norsand rather than Cam Clay type ideas. And this is the map they've come up with, or one map, which they put out in a Tailings conference in 2021. If I have any gripe about this figure, they have a much wider range of partial train behavior, which none of us have touched on yet, than I believe is the case. The reason I think that is so is when in Vancouver, we have had a fair bit of ground improvements. And we know that vibratory ground improvement methods stop working when the cone friction ratio goes above 1%. So that tells me, vibratory methods depend on the sand being pretty free draining or the sandy silt being pretty free draining. And if a vibroflot gets a drain response at 1% friction ratio, I don't believe a CPT is going to go partially drained. So I believe that line must lie in here. On this side, I'm less sure, but again, based on my experience at Bennett, yeah, I'm finishing now, this is my last slide. That's it. So let me just jump ahead 2 slides. Oh, yeah, discuss. Now Simon will answer all the questions.
So maybe we can begin with one question online. I think it's probably for Simon. Do you think that the change in CSL also occur on compacted filtered tailings?
I don't think the CSL changes in compacted tailings. I think the stress dilatancy parameters change. We're actually publishing soon a paper with the UWA guys that speaks to the effect of preparation method and especially compaction. This is something that again, Dave Reed at UWA has been quite passionate about. It really does affect the dilatancy parameters, CHI and in particular. But the critical state line itself, no, I don't believe it does. I think the critical state line is unique in that sense. That's my personal opinion.
Do you have questions from the audience? Yes, maybe we start with you.
Very nice presentations, thank you. I was just, I think this is going to be, we can discuss later, but I wanted to get your initial thoughts. When you were showing the shift on the critical state line for this, I think it was these very laminated materials. So I was just thinking on what could be the fundamental reason for that, because it may be the case that it's not anymore behaving as a continuum, because otherwise, if you're testing the same gradation on the same material, I would tend to think that you should be getting the same critical state line between the initial, material that is having this, fabric, let's call it fabric, and then I think you went and you reconstituted the material again, you test it again. So if in the 2 cases that is behaving as a continuum, so I believe it should be as the same critical state line. Maybe the intact specimen is not kind of behaving as a continuum material, where I would say would be taking even the question further if even we can be talking about defining a critical state line for a material that is having this discontinuity in the middle. Not sure if it's even maybe more like a boundary value problem with boundaries in the middle. So yeah, some thoughts over there. I think that could be a very long conversation.
No, I think you're on the right track. I think there's lots of different theories thrown around, but to tackle it, I think moving towards actually modeling it as discrete layers in, for example, finite element or something to try and understand if there is a difference, or if it's something as simple as just a different packing ratio in terms of where those particles are falling within, to achieve that natural void ratio. But
Millwood started going down that road. He came up with a fractal gradation index because he was suggesting it's the way the available space of the different sized particles pack into each other that matter. I've never seen the fractal index go anywhere, but I think the idea that we look at a particle size distribution curve and say we need to look at the shape of that curve and put some mathematical equations to that and say, okay, we represented that distribution as a distribution of equal sized spheres, you know, how would that shift things?
Yeah.
But bear in mind, all this critical state stuff traces back really to Osborne Reynolds, who said we can idealize soil as steel particles, and that then it all becomes about kinematics, about how they pack and move over each other.
Yeah. So yeah, and just a follow up over there, I'd like to get your thoughts on. Is it even making sense to define a critical state line for a material that is not anymore a continuous and it's having internal, I would say, imposed boundaries? Like I'm thinking about this layering as an internal boundary. So I'm trying to think if even it is making sense to define a critical state line for that. Yes. Again, I'm just thinking aloud, but I'd like to get your thoughts.
How are we doing? Probably a question for both of you, I don't know. So at the moment we design for post-liquefied, well, liquefied strengths. When do you think we'll get to the point where we can design by deformation modelling to assume that we're not going to trigger liquefaction, that we're that confident? So we've got the uncertainties of layering and the lumping that goes into that. We've got the issues of state dependency fabric, partial drainage of understanding of CPT, but there's also the in situ stresses, which is another big question that it's just as important as the rest of it. So
yeah, they're seeing input. I think in some ways we're whipping our own backs because we took the Tar Island case history and when we applied the entire process to Tar Island, we got the extent of liquefaction that nicely matched what the people reported in the day, even though it wasn't really believed in the day. And we got the settlement when it liquefied, it slumped. The measured slump was 5 meters. Our first run on the model, we got a 4-meter prediction. And the reason we didn't get 5 meters is we were making statistical judgments on what was the characteristic state parameter. And my assessment, and we didn't do this formally by saying, you know, producing PDFs. I just put my eyeball on the CPTs, and I said, I reckon the characteristic state parameter is plus 0.065. And my co-author said, Mike, you are full of it. You do not have 3 decimal precision on an estimated state parameter. So we went with 0.06. And if we'd gone with 0.065, I think we'd have nailed the 5 meters on the first pass. So I think we are flagellating ourselves slightly. That also brings up a topic which I skipped on my slide. Sorry, go back a bit. Let me go back. This is something we're not doing, and nobody's mentioned in this workshop, is what about some case histories? What about a bit more analysis? All of us, you know, we're talking about lab testing. You know, how much more can we do in the lab? We're going to hear this afternoon, we're going to talk about finite elements. But nobody is saying, okay, what about case histories? This case history is actually very much like a 1/5 scale Tar Island. What was happening on the top right photo is they're putting a cover over a disused tailings area. The dozer got too close to the edge and it triggered a failure. And the failure, it wasn't a simple rotational failure, it punched out near 10 meters from only a 2 meter height lift. Right? And this looks exactly like Tar Island. So I would say, okay, perhaps we need to talk as a profession about doing some simple failures at not necessarily large scale, but this is a halfway step between centrifuge and real full scale. And I think that should be on our debate table.
I think I have to take 2 questions from the online folks because we didn't get an opportunity to meet you during lunch. So, Louis online, Mike, it's a question for you. I believe the Wiget requires you to distinguish between drained and undrained CPT. How do you recommend we make that distinction? And there is also a question for Simon. To make your in-situ state parameter estimates, how did you measure or estimate the horizontal stress?
You go first.
Horizontal stress in that case was an assumption of K naught. And I think all of us recognize there are improvements needed in the ability to estimate or measure in situ stresses, and it's something that I'm quite excited to hear about with, as the pressure meter, for example, gets more use and more application. I think, for now, most of us are looking at sensitivities to K naught, so what we'll do is assume something like 0.6 and vary it to check that the sensitivity isn't something that's changing the fundamental answer, but it's an assumption.
Okay, on the question of how I pick undrained versus drained, well, the first answer is it comes out of the CPT data itself. If you take an entire CPT trace and you plot measured BQ versus soil behavior type index, where you've got drained, the BQ will be 0. It will sit nicely on the axis. When you run up to a BQ around 2.3, all of a sudden you'll start finding some readings of positive BQs. When you get to a soil behavior type of, say, around 2.6, you'll have just a raft of everything with significant undrained response. So the CPT almost tells you, if you plot its data up in a normalized form, and it will vary with the soil, because don't forget, we don't have the same CV at each site, but it will tell you for your site where the bandwidth is between clearly undrained and clearly drained, and then that's how you can then go back to one of these charts and say, okay, for my site on a soil behavior type diagram, that's my partially drained area. And part of his PhD is a method for how you take the widget and use it in partially drained situations. So again, when you've figured it out, call the UWA folks.
So can we take this over lunch, or you people are sporty enough to take another question? Okay, so.
I'm happy to take more questions. I'll stay here if you don't want to record them.
Thank you. Okay, I'm wondering what happened when you shifted the critical state line with one sample, with one test, and you shifted in the way that you are increasing the P 10 times after the shift. So the undrained strengths increased 10 times. So as a practitioner, I'm a practitioner, you are very brave to do that. And how can you support that, how may I say, judgment or final decision? It's not easy.
Well, what we did was we shifted the critical state line to match the endpoint of that test, but it didn't affect the interpretation because, as I said, the cavity expansion is not sensitive to the position of the critical state line. So it doesn't affect the strength. The strength is as it would otherwise be interpreted. So what I'm presenting here is in terms of the in situ characterization of the state parameter, but when it comes to interpretation of residual strength, for example, which is where we ended up going to once we'd identified where this material was potentially contracted and potentially dilatant, those methods followed typical. So it didn't affect the strength because, again, it's what we're looking at is the state parameter, which is not sensitive. It's moving with the critical state line, so it didn't affect it. So there isn't a change in strength that comes from it. I could explain that further maybe over lunch, but the strength doesn't change.
Yeah, it's easy to think. It comes out that the CPT is a mechanical test, right? If it's telling you the soil's dilating, just be happy with that. That's what you're actually measuring with the CPT, is the amount of dilation. We want to put it into critical state terms because we want to use it, estimated residual strengths and everything else. But in essence, what the CPT measures is the effective dilation given the compressibility of the soil you're dealing with. It's as simple as that. But I would also add that I think you have a very fair point. How do you add confidence to that? Well, I'd say the answer is maybe consider using a pressure meter. Because the cone is a large strain test. A pressure meter allows you to go in and look at detail. That's relatively small strain. So you can look at the stiffness, you look how the strength is evolving. So if you've got a large dollar decision, maybe you should call Cambridge in situ and do a few pressure tests. And Yasmin, the bill's coming.
So I think that brings us to the end of this stimulating session. Hopefully not people are not upset with starting a late lunch, but we have another 45 minutes for lunch and we'll see you online in another 45 minutes.
Please take a seat, and we can move forward to the next session. That is going to be about numerical modeling of tailings dams. We are going to have 3 presentations. So this session is 1 hour and a half, and then we're going to have a discussion. So the setting is we do the 3 presentations in a row, and then we're going to have a common discussion at the very end. So I'm going to let the speakers know. The speakers have 25 minutes-ish. I'm going to tell them when 3 minutes are remaining. Well, the 3 minutes is just a signal to say that we need to go to conclusions. The first speaker of this session is Professor Michael Hicks from TU Delft, Netherlands. He's a distinguished professor with almost 4 decades of experience leading Delft University of Technology's geoengineering session. The floor is yours. Thank you very much.
Okay, thank you very much. I'll put my watch here. I'll try and keep on time if I can. I'm standing in the right position, hopefully, for the screen. Okay, great. So yes, this is an outline of my presentation, and I guess it's slightly different from most, if not all, the other presentations in this workshop, in that I'm actually not going to talk about analyzing tailings dams or mine tailings. What I'm actually going to do is talk about aspects of slope stability modeling in general and highlight things which I think are applicable to tailings dams. So as you can see here, it briefly focuses a bit on static liquefaction, or the modeling of static liquefaction, and then the influence of spatial variability on static liquefaction. I talk a bit about cyclic mobility, and then I focus on the influence of spatial variability on the initiation, propagation, and extent of slope instability. And when I do that, I'm not specifically talking about liquefaction, I'm talking about slope instability in general, for general materials. And then I'll have a few concluding comments before I finish with just a few slides to illustrate one of the recent research projects we've had looking at flow slides. So I'm going to start off a very long time ago. I try not to think about how long ago this was, but this must be 35 years ago or something. This is when we looked at the failure of the Nurlik underwater berm, which I think many of you are familiar with. And the Nurlik underwater berm was part of a bottom-founded offshore oil exploration platform in the Beaufort Sea off the north coast of Canada. And the water depth in this particular area was 46 meters, so the Nurlik berm was designed to be 36 meters high. But because of the water depth, there were 2 critical things about the design which made it a bit different. The first is that they used a local burrow source to construct the berm. And the second thing was that the weak clay layer on the seabed wasn't removed prior to construction of the berm. And to cut a long story short, the berm failed during construction due to static liquefaction when the berm had reached a height of 26 meters. And so the first thing we looked at was, what are the possible trigger mechanisms for this static liquefaction case history? Here are some examples of the calibration we did for our constitutive model to the Nurlik sand in a loose and liquefiable state. So these are CRU test calibrations. And the thing I want to highlight in this is that the strength loss that you can see is caused by compressive pore pressure changes which arise due to the suppression of volume decrease during shearing. So there's absolutely no strain softening in this whatsoever. You can see, in fact, if you look at the stress paths on the left, the mobilized friction angle is increasing all the way around the stress path. So this decrease in load carrying capacity is due to the compressive pore pressure changes. Okay, so assuming the Nurlik fill to be in a loose and liquefiable state, which is quite reasonable, seeing as we had a liquefaction failure occurring, we looked at various trigger mechanisms. We looked at the possibility of rapid loading causing liquefaction in the Nurlik fill itself. We looked at the possibility of deep sliding through the underlying weak clay layer. But what we found to be the most likely mechanism, interestingly, was a combined mechanism. It was a combination of rapid deposition as the berm was constructed and limited movements in the underlying weak clay layer, triggering liquefaction in the upper half of the Nurlik berm. And so this is interesting because it involves interaction between different parts of the structure and is a very good illustration, I suppose, of why you need numerical modeling to look at this sort of thing rather than, for example, limit equilibrium methods. However, despite this particular finding, there was one question still outstanding, and that was that we had assumed, not unreasonably, that the sand was in a loose and liquefiable state, whereas CPT data had suggested that the fill was predominantly dilative. So this led us on to a sort of a follow-up investigation where we took account of the fact that the state parameter was varying spatially throughout the berm, and that we had behaviors ranging from liquefiable right the way through to strongly dilative. The thing about heterogeneity is that it affects material behavior. It affects the global response of the structure. And so, of course, what we're interested in is, well, what single value, for example, of the state parameter is representative of this spatially variable structure? And what you find, of course, is that the spatial correlation scales of the heterogeneity are quite important in determining the relevant characteristic value. But anyway, what we found was that it was certainly possible to take the CPT data for the site, the predominantly dilative data, and it was possible to get liquefaction through this predominantly dilative fill due to liquefaction through semi-continuous weaker zones which have been formed during the construction process. And so what we basically found was that the stability of this structure was governed by the weakest 5 percentile of the material. This is a much more recent thing. This is a project we're still working on. This one doesn't involve slope stability, but I thought I would show it you because it is quite a nice illustration of dealing with spatial variability or heterogeneity. And it concerns the Groningen region in the north of the Netherlands, where they have been taking shale gas out of the ground, and this has caused induced seismicity, which they're not terribly happy about in Groningen because some people's houses have been cracking. So this is investigating the influence of the shallow subsurface on the amount of energy transfer to the ground surface due to the induced seismicity. It's also looking at the potential for liquefaction in laminated sand layers that appear in Groningen as well. And this particular project involves spatial variability at 3 different scales. So we first of all have the small scale, where we have, for example, laminations in the sand or fibers in the peat, for example. Then we have the mesoscale, where we have spatial variability within each geological unit. And then, of course, we have the spatial variability with respect to the distribution of the different geological units. And so what we've done is we've taken account of this heterogeneity at the small scale through the constitutive modeling, and then we've taken account of the spatial variability at the mesoscale and at the macro scale by using, for example, random fields. So this is an example of the constitutive modeling. This is looking at the model that we have been developing for the laminated sand. And basically what it is it's being constructed within a multi-laminate framework using bounding plasticity. And it takes account of the anisotropic fabric of the material and the evolution of the fabric during the shearing process as well. So it's really quite a sophisticated model. And we have a monotonic version of the model, which we published in Geotechnical, I think it was earlier this year, and a cyclic version of the model, which we should be submitting for review fairly soon. In this picture here, the circles on the upper right showing the various surfaces are a little bit misleading because once you take account of all the different planes in this multi-laminate model, the actual yield and failure surfaces don't look anything like that. They actually look more like a rounded, more cool or more Matsuoka Nakai surface. Once you've integrated all the planes up, I think we use 32 planes normally for this model. So that's at the small scale. Then at the meso and macro scale, we need to characterize statistically the ground, both the heterogeneity within layers and also where the various geological units are themselves. And I suppose we tend to have a three-pronged attack on this for the various projects that we look at. The top right-hand picture is showing you where we use closely spaced CPTs. This was for a dike stability assessment, but this is showing closely spaced CPTs to try and characterize the spatial variability in the vertical direction and in the horizontal plane. And in that picture there, some of our CPTs are spaced by 1.25 meters, so they're really close CPTs. Then the picture down the bottom, is, now this is from the Groningen region, I think. This is where we've got 5 boreholes, and we're using Bayesian modeling to try and get the most likely profile at each particular borehole with respect to the different units. And then I think we use coupled Markov chains to predict the spatial variability between the boreholes. So the bottom left is looking more at the identifying the variability of the geological unit. And on the right, you can see this is work we do in conjunction with geophysics at TU Delft. And basically, the idea is to find the correlation between CPT data and shallow geophysical data to help us in characterizing the ground. So we do lots of different things to try and characterize the spatial variability. And this is just an example of some initial analysis we did looking at the influence of spatial variability on liquefaction potential. Basically, what you can see on the right here, we have 2 columns. Each column is a different realization looking at the initiation and progression of liquefaction due to an earthquake. And what you find is that the spatial variability of material properties in our sand layer greatly affects the liquefaction potential, but also greatly affects the spatial extent of the soil liquefaction and the peak ground accelerations that you measure at the ground surface. And what it really highlights is that you definitely need to use at least a 2D analysis, if not a 3D analysis. If you use a 1D analysis, then the extent of the liquefied zone and what you predict at the ground surface is completely wrong. So you need to use at least a 2D analysis. Okay, this slide is an introduction to another piece of work that we do quite a bit on. This is looking at regional dikes in the Netherlands. These are secondary dikes as opposed to primary sea defense dikes. And in this diagram here, what you can see on the vertical axis is required global factor of safety against slope instability, ranging from 0.5 to 2 on the vertical axis. And then on the horizontal axis, you can see different periods of time. On the left, it's 1973, and on the right-hand side, I think it's 2009. And in this diagram here, red indicates unacceptable factor of safety. Green indicates acceptable factor of safety. And yellow and orange, well, it may or may not be okay. It depends upon the situation. And what you can see from this diagram is that there is considerable uncertainty about what the global factor of safety should actually be. So what we do in Delft is we look a lot at uncertainty, one of the methods we use most is something called the random finite element method to take account of uncertainty with regard to stability of slopes. And the random finite element method is essentially a Monte Carlo analysis, where in each realization of your Monte Carlo analysis, you are basically using random field theory to predict the spatial variability of properties and finite elements to compute the response. And the idea is that you carry out this Monte Carlo analysis, you get lots of possible solutions for the problem. And so what you end up doing is you end up representing the stability of your structure, not in terms of a single factor of safety, but in terms of reliability, the probability that failure will not occur. So in this flow diagram here, you can see that we start off with our site investigation, we characterize the site, and then in each realization of our Monte Carlo analysis, we generate a numerical prediction for the spatial variability of properties within each layer. We may also have, we probably also will have to have a prediction for where the interlayer boundaries actually are. And we may even take account of uncertainty in the external geometry of the structure as well. And then what we do is we carry out a finite element analysis to get the response of the structure. And then we do the whole thing over and over again using the same input statistics to get the whole range of solutions you can see at the bottom right-hand side for the factors of safety. And in this picture here, the probability of failure, of course, is the area underneath this PDF to the left of F equals 1.0. Now, of course, we've got quite a large range of solutions there, but we can reduce the uncertainty by getting more site investigation data, more laboratory data, or maybe monitoring data, including during the lifetime of the structure. And we can also cross-correlate between different data sources. And of course, if we gain more knowledge about the proper transformation between measurements and properties, that also is reducing uncertainty as well. So all these things reduce uncertainty. And as we reduce the uncertainty, the width of this distribution down here becomes narrower. And as this distribution becomes narrower, what you'll probably find is that the reliability goes up. It's not guaranteed to go up. You may be unlucky. It may actually go down. But usually it goes up. So by getting this extra data, usually you can end up with a much more efficient solution. This is asking the question, 2D or 3D analysis. And there's quite a lot on this picture, so I'll try and keep it brief. But basically, what we're looking at here, what we're looking at is a slope which is very long in the third dimension, so a bit like a long railway embankment or dike, for example. And on the vertical axis, we've got reliability as a percentage. And on the horizontal axis, in this case, we've got factor of safety based upon the mean property value. So we're finding, or we're getting a generic response for the relationship between reliability and factor of safety based upon the mean. And I've highlighted 3 curves here, corresponding to 3 different categories, if you like, of failure mode. And these categories are related to the scale of fluctuation, the correlation distance, and the size of the problem. If your scale of fluctuation is very, very small in all directions, what you'll find is that the response of the embankment is a bit like a homogeneous material based upon the mean. And then what you can see is that the reliability jumps from 0% to 100% as you pass through a factor of safety of 1.0, as you might expect. If, on the other hand, you have a very large scale of fluctuation in the horizontal direction so that your heterogeneity is almost layered, then what you'll find is, again, you'll get this sort of failure along the length of the embankment, but now you have a much wider range of solutions shown by this wide gray distribution. The thing about both of those gray distributions is they are essentially 2-dimensional solutions. In contrast, if you have an intermediate scale of fluctuation, you'll end up with a 3D failure. And of course, in reality, virtually all the failures will be 3-dimensional. And when you take account of the 3-dimensionality, you get this red distribution shown in here. The thing to realize is that whereas the other 2 solutions are 2-dimensional and therefore slope length independent, the 3D solution is slope length dependent. The longer the slope in the third dimension, the more likely it is that you'll encounter a zone which is weak enough to actually trigger the failure. And so as the slope gets longer and longer and longer, the computed reliability gets less and less and less. The other thing is that when you have a 3D failure, or when you take account of heterogeneity in 3D, there's a much larger range of possible mechanisms than you would get in a 2D analysis. And these two things, the slope length dependency and the number of potential failure mechanisms, mean that sometimes you might find that the 2D solution is actually not the most conservative. This is a sort of a follow-up to or another aspect of the work we do on dike stability. And in this particular picture here, what we're investigating is what happens after the first slide. Is it then possible for another slide to occur and then another slide to occur? And in this picture here, we have 6 realizations of the spatial variability in our dike. And they've all been produced using exactly the same set of statistics for the material property. But each one, of course, each realization gives a slightly different distribution of the strong and the weak zones, which means you get a different response for each of these 6 realizations. The top one doesn't lead to any instability of the dike, whereas the other 5 do fail. And what you can see is that in the case here, we have 1 failure occurring. The next one down is also 1 failure. It's just a bigger failure in this case. But again, it doesn't actually lead to flooding. Now this one down here, the 4th one down, we have 1 slide occurring, and then we have a 2nd slide occurring. But again, it doesn't lead to flooding. Whereas the 5th one down, you can see, actually does lead to flooding. So here we have retrogressive failure leading to flooding. The one at the bottom is quite interesting, because the one at the bottom, you've got a slide occurring. It doesn't actually reach the crest, but the amount of soil that's still left there is not sufficient to withstand horizontal sliding along this weak zone you can see near the base of the dike, and you get flooding. So the question is, when has the dike failed? Has it failed when you get a slope instability, which is basically what we say at the moment in the Netherlands? Once you get a slope instability, it's failed. Or do you say, well, no, it hasn't really failed because we can come along and we can repair it? So maybe slope instability is just reaching the serviceability limit state. Maybe what we should do is we should take account of the residual resistance that's possible after initial slope instability and take it and say, well, failure is really when flooding occurs. So that's the sort of work we've been doing here. We've been looking at residual dike strength, what strength is left after the initial slope failure, and raising the possibility that we could define failure for these structures, not in terms of when the slope experiences a slide, but when flooding actually occurs. This is just showing the same sort of thing in 3 dimensions. The left one, you can see a sort of a regressive failure where you get 1 slide and then another slide and then another slide. The one on the right is more kind of a failure where it becomes unstable and then the unstable zone spreads and you get more of a flow slide type thing. And so what I've said down here is that the initial evolution and general character of the failure mechanism is heavily influenced by the nature of the spatial variability and by the type of soil behavior, because what I'm showing you in these pictures here is just the influence of the spatial characteristics. I'm not actually looking at the type of soil behavior. This is for a strain softening soil. It's not for soil liquefaction. And of course, if you have a liquefiable soil, you'll get something different again. Okay, I've only got a few minutes left, so I'll go through these and just, I mean, I think I've probably, I won't go through all these because I think I've covered them fairly comprehensively already. But obviously, soil heterogeneity has a big influence on soil behavior, on the initial and evolution of failure mechanisms. It highlights the need for 3D analysis, and soil heterogeneity is obviously a major source of uncertainty and highlights the need for a reliability-based approach to slope stability assessments. And I've mentioned down here that there's a need for proper validation of constitutive and numerical models, which just leads on to the last few simple slides. And this is another project we've worked on quite recently at TU Delft. This is the Oosterschelde storm surge barrier. And the thing about this barrier is that when the water passes through the gates, it speeds up because there's less space for the water to travel. And so what happens is that when the water gets to the end of this kind of cover layer on the riverbed, it scours out a hole, which they knew about in the design, but no one thought that these holes would get to be 30 to 50 meters deep, which is what they are at the moment. And you've got to remember that the water here is about 20 meters deep. So this means our underwater slopes are up to 70 meters high. And what they find is that every year they get big underwater slides occurring. They can see it from satellite imaging. And so they've been worrying about what to do about this particular problem. This is a large physical modeling facility we've got at TU Delft, which was basically paid for by the Research Council and partly by Boskalis, Owen Rijkswaterstaat. And it's for investigating in the laboratory underwater slope liquefaction. It's 5 meters by 2 meters by 2 meters. We can trigger liquefaction by rotating the tank and causing liquefaction in a horizontal sand bed. Or what we can do is we can use this dredging system you can see on the right, excavate out a slope, and then trigger liquefaction by injecting water at the base of the model or putting external loadings on the model. And from that, we get a lot of very detailed data coming out. So this is the sort of thing we want to do. Obviously, we want to upscale what we see in the laboratory to the real situation. I've got a very crude sort of flow chart at the bottom here. The idea is that we basically take our constitutive models, we calibrate them against triaxial data on samples which have been prepared in the same way as the sand in the tank has been prepared. And then we use those considered models to analyze the tank experiments. And in these experiments, we have lots and lots of detailed data on accelerations and pore pressure changes leading up to liquefaction failure. And then having validated those models, then use them to look at the real situation. Okay, so I think I have, it may have taken 26 minutes. But anyway, that is the end of my presentation. Thank you.
Thank you very much for the very nice presentation. So as I said, we keep going with the second speaker, and then we are going to have the third speaker, and then questions and discussion at the end. Next speaker is Hans-Petter Jostad from NGI. He is technical director at NGI with over 30 years of expertise in numerical modeling of geomaterials, particularly complex strain softening mechanisms. The floor is yours, Hans-Petter.
Thank you. So, welcome to this presentation. I don't think it is my presentation yet, but let's see whether it's coming up. There you are. Very good. So I'm going to talking about how to do stability analysis, and then first of all using more advanced method like using finite element methods. Of course, it is not me that has been doing most of the work that I'm going to present. We have Sparsa that is here, and we have Øyvind that is here. So they also can answer questions maybe afterwards. The outline of this presentation is that I will start by showing some simple stability evaluation, because if you are going to do more advanced, it is important that you understand the mechanism, and by using more simple methods is a good way of really understanding what is the key problem. Then I will go into finite element analysis. I will use the Fondao dam failure as an example, because I guess several of you actually know a lot about that. And I think it is a good example for demonstrating what we can do by using finite element methods. So I will talking about material models, starting with very simple models like the Moore-Coulomb models, going a little bit more to advanced models like the Praxis hardening soil model. And at the end, which is the main purpose here, is to demonstrate the benefit of using more advanced models like critical state-based models, like has been discussed in several of the presentations before me. I will also mention in a little bit about stage construction and drainage, which is important for this type of problem. And at the end, I will demonstrate how we can do static liquefaction analysis by using finite element method. Okay, starting then with the simple problem, a stability of an idealized dam. And let's see. So what is the key input parameters of this? It is the height of the dam, it is the inclination of the dam, we have the driving forces, that is the weight of it, and of course we need the strength, and we have the phreatic surface. So that is in a way the key parameters. We need to assume a critical failure surface. Here it is assumed a very idealized one. This is a kind of active earth pressure, so that means a very idealized failure here. And then we have slip along the bottom here. Of course, it is not necessarily the most critical one, but it is an easy way to see how the different parameters is affecting the stability. And you can set up then equations, quite simple equations like this. This is then the driving force, including in a way that you end up having some resistance here that is reducing this horizontal pressure. And we see that these different horizontal stresses depends on whether you have drain condition, where you are modifying the effective horizontal stresses by the friction angle according to this equation, or if you have undrained condition, where this horizontal stress factor is equal to the vertical minus 2 times the undrained strength, and then divided by the vertical stress. So this is an easy way, and you can then see how much effect you have by changing the height of the dam, how large effect you have by changing this inclination factor, and specifically what is the effect of changing the phreatic surface. So quite interesting, and I'm going to use this very simple equation to compare it with more advanced analysis, and it gives a good agreement. Of course, not exact value, but you see what is governing the problem. Of course, you can also use other simple methods like stability charts, like the one here that was proposed by Jambu in 1973. What he is doing is assuming a circular slip surface if it is undrained, and you can go also in here to find what factor and how different parameters is affecting this stability. Like also here, the inclination number, the height, and also how deep this failure surface is. Nice in a way to see and start to understand what is the problem and what you should expect as a stability. Then I will continue to go into this example of the Fondao Dam failure that occurred in 2015. I'm not sure whether you are able to understand how this looks like, but you see here the dam here. This is the bottom of the dam, and this is then the top of it. And we are talking about the right and left side of it, and the reason for that is that a lot of problem occurred here on this side, and failure, according to observation, was taking place on this side. Of course, the failure occurred with liquefaction because almost all of the material was flowing out after the failure. So it was clear that this was a failure that was a static liquefaction type of failure. If you're talking about triggering, there was not any clear trigger that was identified before the failure. There was some small earthquake 90 minutes before. They were small. Whether that was enough or not is, of course, a question, but otherwise not any clear triggering. If we're talking about a tailings material here it is more like a sand-sized with silt particles, and of course it is loose, and it is clear that this material can liquefy if it is loose enough. In addition, we have the slimes, which is more like a clay-like type with lower permeability. And what was important is that these slimes was located in areas where it should not be. Okay. What will be based on here on all the input parameters and so on is taking from this very good report from the review panel that was led by Professor Morgenstern. So it means that all parameters is taken from that. We have checked it a little bit with our own database, but most of it was taken from this report. The panel, of course, in addition to try to explain the reason for the failure, they needed to answer these quite interesting 3 questions. Why did the flow slide occur? Of course, important. But why did the flow slide occur when where it did? So it means that on this left side compared to the right side, and why did the flow slide occur when it did? Also quite interesting. I guess several of you have already maybe been reading this conclusion that they had, the reason for this failure mechanism. They are related to these slimes that they say was loaded and compressed, but at the same time, when you compress it vertically, it expands laterally. So then they say that it was squeezing out like a toothpaste in a tube, and a process of what we call a lateral failure, like lateral extrusion. This extrusion is reducing the horizontal stresses in the sand above, and then was loosening the sand, and this was then the reason for the failure. So that was the explanation. But let's see what happened if we now start to dig a little bit more into this by finite element analysis to see whether we can understand this mechanism a little bit better. This gives a good view of a vertical cross-section through where the failure took place. That is in a way on this side. This is not going all the way to the toe of the dam, so it means that the height of the dam in this cross-section is only 56 meters. We see here these slimes that is located here at the bottom, but also several other layers, so quite interesting. We see here also pictures of the different materials. We have the sand tailings and we have the slimes. Also interesting was that due to other problems, they needed in a way to move this dam backwards in a way to increase the stability. But the consequence of that was that they started to construct the dam on top of these slimes. We also see some other effects that they try to put a berm on top of here in this area, also to try to increase the stability. Another thing is, of course, to look into the rate of construction. So this shows in a way the elevation, or say the height of the dam as function of time. And we see that the construction rate is varying somewhat. In this area, it is 18.5 meters per year. But interesting is to see at the end, then actually the construction rate is quite high, and it is higher than what it has been before. And we're talking about something that is a construction rate of almost 30 meters per year at the end. So that may have some consequence for this, especially regarding drainage condition. Another important input parameter to a finite element analysis is the location of the phreatic surface. And we see that at the time before it fails, the phreatic surface was quite high. So that is important, but another thing is that there was not any clear indication that the phreatic surface was increasing before failure. So it was high, but not necessarily increasing. So not necessarily the mechanism that was triggering the failure. Main properties of this, we're talking about a unit weight of 22 kilonewtons per cubic meters. We have a friction angle of 33 degrees for the loose sand tailings. We have some higher friction angle for the compacted part of the sand that is constructing the dam, also with some small cohesion. And we see the slimes has a lower friction angle of 28 degrees. So This we can then put into a finite element. We could have used the limit equilibrium methods, but here I used the finite element method. So putting in these friction angles and cohesions for the different part of the materials or different zone, and do what we call the C-phi reduction calculation to reduce the friction angle and cohesion until it fails. And we ended up with a safety factor that was as high as 2. So of course then, question then, how can actually this dam fail when we have a safety factor of 2? Quite interesting, because it is not close to failure, it is quite high. So we need, in a way, to start thinking in a different way, and of course then, it is that this is drained. We were seeing that failure took place like static liquefaction, so we need something that is transferring this behavior from a drained state to an undrained state. That is important. And then I will start looking into that. And the reason for this, that it is important to go to that, is of course we see that, okay, this is a test that is drained, that gives this friction angle. But if we then do undrained tests and do that for different void ratios, we see that for some critical void ratio, we start to have this critical contraction, as that has been shown in several of the presentations before. And we start to see that, okay, this causes a reduction in the shear stresses, and it actually goes almost down to 0, or actually down to 0 strength. Maybe easier to see in this plot where we have the deviatoric stress versus the axial strain. So this is then the drain test, and we see the undrain. We have a peak value, but after that, this shear stresses is reducing quite rapidly, and it actually goes down to a residual strength of 0. So it becomes totally liquefied. And what is interesting when you start to have these people that are familiar with strain softening, of course this is strain softening if we assume undrained condition, is that you can start to have what we call the progressive type of failure. We are not necessarily putting in just the peak strength into it. It can start at a place and it gradually start to developing a failure mode. But still, the question is, we have this totally different behavior, but we need to go from drained condition to undrained condition. So that needs to still be studied. This is just some presented factor of safety. We see that also they was calculating a safety factor for fully drained condition close to this 2, here it is 1.9. And we see that if we have an undrained strength divided by the vertical stress of 0.25, we end up with a safety factor of 1. So that is what we need in average to have this one to fail. This is then some input parameters that we need into the models. We have drain test, we have the volumetric strain versus axial strain that gives us the latency parameter. We had, that is shown in a lot of presentation, what is the critical void ratio as function of mean stress, and we have some odometer test that also gives us the compressibility. It was given some values in the report. One need to be a little bit careful because some of this value was wrong, so that one needed to dig a little bit more into it to find what was the correct values. But then for the sand, I found that maybe this was looking more realistic, that you have a permeability of in this range. And based on the odometer modulus, you can calculate the coefficient of consolidation that gives something in the order of 300 square meters per day, or 16 meters per hour. What that tells you is that the sand is drained during operation. You are not generating any pore pressure at all, even with this high construction rate at the end. But still, if failure takes place within something that is less than an hour, you can still have undrained condition at failure. If you look into the slimes, then it is a little bit more interesting. We see that then we have a CV that is 50 square meters per year. And if you put that into this famous equation where the time for almost full drainage is equal to the square of the drainage distance divided by this CV value. So then you can calculate that, okay, it is able to fully drain something that is a layer that has a thickness of 2 to 3 meters per month. But that gives an indication that you have partially drainage, at least can have partial drainage during construction. Yeah, this was just to find what kind of permeability one should use in this calculation, and we see that the difference in permeability between the slimes and the sand is of a magnitude of 3 magnitudes smaller in the slimes compared to the sand. And we needed them to check, since it was a little bit unclear, this permeability, so we checked with our own database, and also there it fits quite well that we have talking about this type of range of permeabilities. Then the odometer modulus, in order to calculate what is the drainage condition, we have some odometer test of the slimes, some on the sand. We see that the odometer modulus is increasing more or less linearly with the vertical stress, both for the sand and for the slimes. And we see that this difference in stiffness is only a factor of about 2. So not 7 minutes. Okay, good. So it means that there are not significant difference, but still it is a difference. The main difference is the permeability. This is then a consolidation analysis. It is then used the full model at the end. So this was how it was looking at before failure, and it is just applied an arbitrary load on top of it. And this load is increased by 30 kilopascal during a period of 30 days, and that was something that is similar to the high or the rate of increasing the dam height or the construction rate. We see that the slimes becomes then more or less undrained in this area. But also we see that we have a sand layer in between here. And we see that there we end up with pore pressure response in between this slimes layer. So that can be one potential triggering mechanism. That, okay, we were seeing that the sand in itself was fully drained, but when it is interlocked between 2 slimes layers, we start to have some pore pressure response also in the sand. Another interesting things that we need to look into, it is what is the mobilization before failure. So that means, what is the stress ratio in different areas? Where can this failure actually be initiated? We was showing in some of the presentation early today that we need to have a given mobilization before we can end up with this type of instability. And we were seeing that, okay, we had some high mobilization in this area and also in this area between these slimes layer. Here we're talking about actually a mobilization that is more than 80% of the peak strength. So something in between 80 and 85%. But it is interesting to see what type of stress do we have in this area. And we see that the maximum principal stress is still close to vertical, even if this interbedded layer. So it means that there are very small horizontal shear stresses. Of course, if we have had high mobilization here of a horizontal shear stress, that will be very critical, because then if you start having softening in that part, you may have progressive type of failure. But if you have this type of condition, it's not so easy to thinking about the progressive type of failure, because what happens when you start going above the peak and start reducing the shear stresses? Actually, what you need to do, either you need to reduce the vertical stresses or increasing the horizontal stresses, or both. And if you increase the horizontal stresses in this area, you are not automatically ending up that you end up with higher mobilization in the zone around. Actually, it is opposite. So you don't triggering a progressive type of failure in this interbedded layer here due to softening. So Another thing is, of course, to look into this stress ratio. Where can you actually have your initial triggering is important. So it was also studied whether the effect of doing this in stage construction or actually taking your configuration at the end and apply gravity loading, giving the same mobilization. And we see that it is not, so it's not very sensitive to different type of input. We end up more or less having the same area where we have the highest mobilization. This is then with just gravity loading, and this is with stage construction. And you can also play with the different stiffnesses and uncertainties to see how much it is affecting this initial mobilization. Then the static liquefaction, we need a good constitutive model to be able to model this stress path that depends on the different void ratio. So we selected to use the SANISAN model, that is a critical state-based model. The reason for that was that at that time, that was the only one we had available. We could have used NORSAN, that is available now, but at that time, we was in a way needed to use the SAN model because that was the only model we had available in Plaxis. But still, the advantage of this model is that it is handle these critical states. We can go from something that is loose and handle loose material. And in addition, we have very well control of the latency, so we can model this stress and void-dependent contraction of the different material. This is some examples showing how it is calibrated. So we see that, okay, we obtain this peak value and this softening. We see the stress path there isotropically consolidated, but what is important is that, okay, no, sorry, then I need to go back. How much time do I have left? Probably 5 minutes. 5 minutes. Okay, good, good. Often we're talking about, when we're talking about undrained strength, and we normalized by the vertical, but often that is obtained by isotropically consolidated test. But of course, we see in the dam, in the area where you actually start to have your initial failure, is not in a state of isotropic. There we were seeing that we have a high initial mobilization that is under drain condition. What is advantage by using this type of more advanced model, like the SANISAN model, is that, okay, we can calibrate the model based on this type of test, but in reality, we have a drained mobilization that is quite high, so it means that we start up here, and then the question, what is then the undrained strength when you start shearing from that point? First of all, it is not equal to this undrained strength, so we cannot talking about that the material has a given undrained strength. That depends actually on the stress condition, what is the undrained strength. And that is demonstrated here. Another thing is that, okay, we see that even if the mobilization here, drained mobilization is high, we still have some left. We need to increase the stress is somewhat in a way to come up to this instability point. That can be a limitation in the model, so you need maybe to study different models, whether that happened or not. Because as I say, we need in a way to go from a drain condition to something that directly becomes unstable. So I will come back to this. What is the consequence of that you need actually to increase the shear stresses somewhat there? Then it comes to how to do this type of stability analysis by using a more advanced model. First, we need to establish this stress state before failure. That is the important part, because that tells you where this failure is initiated. You can do this by drained or partially drained and stage construction, depending on your problem. When you have established this stress state before failure, you need to check the stability of it. And one way of checking the stability of this state is to apply an undrained load perturbation. That can, for instance, be an increase in gravity. It can be increased in horizontal gravity, if you won't think it is due to some earthquake, or it can be some load perturbation. The only thing is that you apply something that is small and then see whether it can, what happens if you apply a small perturbation. Then you scale this perturbation until you reach an instability point. You need maybe some arc length method in a way to come up with this value, because it starts to be difficult to obtain the maximum point. And you can continue after this first instability point. Then you need definitely the arc length control to see how this failure is progressively developing. So that is illustrated by this plot, where we first apply the gravity, that is the weight of the material. Then we switch to undrained condition and continue to increase the gravity on the undrained condition until we come to an instability point. And we see then how the failure is then progressively developed after that. And of course, how stable it is depends on how much load you need to apply to check this. So in reality, we want just a very small perturbation if we assume that failure is going to take place. So here it is used, this. We started here with this, where we see that this is the area that we have the highest mobilization at the beginning. Then the gravity is gradually increased until we come to this instability point, and then it gradually starts to decrease. And what we see is happening is that, okay, in this area where we have the highest mobilization, then the strain is continued to increase. It becomes more and more localized, and at the end, it creates a shear band. In addition, of course, when you create a shear band, you are generating a lot of pore pressure. This was a fully undrained condition. You could have done it also partially drained. Then the pore pressure generated in this area where you start having softening may dissipate also into the other areas and increasing and make maybe this process even more rapid. So this is then what we ended up as a failure mechanism of this. And then I come to the final conclusions of this. We see that failure of tailings dams are generally very complex. We have complex geometries. We have complex pore pressure field, if we start looking into that. We generally have complex histories. And we see that we need quite complex material models. The triggering mechanism is complex. And the question is still, how to make this transition from a drained condition until something that becomes undrained or partially drained, which is what you need in a way to go into this static liquefaction problem. And it is shown that this can be done, can be analyzed by using the finite element method. We need a suitable constitutive model. I will say that we need something that is based on critical state-based. We may need couple analysis, we may need stage construction, and as I showed, we can check the stability by applying a small perturbation in undrained condition. And to following the process afterwards, you need some arc length control or accounting from some inertia effects to balance this reduction in the resistance compared to the driving force. So then, thank you for your attention.
Thank you very much for your very clear presentation. And we move with the next speaker, and then we are going to have a small discussion with questions for all the speakers.
Do you have the...
Yes, now he's here.
Here? Oh,
so next speaker is Dr. Ramon Verdugo from CMGI, Chile, and is academic and consultant with more than 30 years of experience in geotechnical engineering, soil dynamics, seismic stability, and co-founding of CMGI.
No, more experience means a very old guy. Thank you. Okay, I'm going to talk about the static liquefaction and main issues. The outline is, I will talk about the quasi-steady state. That was the reason because I asked to Jorge about this. The effect of fabric on the quasi-steady state and critical state in a stability line, state parameter considering the quasi-steady state. And one issue that I think it's very important is state parameter considering a static shear. So probably we will discuss with Mike about this. So I will provoke you. An additional or
parallel steady state, state index, the flow state index. So this thing started probably with the result of Castro, where he tested a triaxial test sun under a low control test. He applied dead weight in the sample, and suddenly, after 40 minutes of applying this dead weight, the sample collapsed, and in 0.18 seconds, the sample reached 20% of axial deformation and a tremendous amount of pole pressure. And when you run control tests or low control test, you have inertial forces because the sample collapsed in less than 1 second. Okay? So what he did is he had a transducer to measure the axial force at the bottom of the sample. So this is the sample, and the load that the sample or the soil is able to transmit will be measured by this low pressure transducer. So this is a very important thing. These tests are from 1969. It's very old, but I have seen many tests where the people are measuring using low control tests with the load cell at the top of the sample. And when the sample collapses in only not a few seconds, 0.2 seconds, inertial forces appear, and people the data that you are getting are not really the forces that the sample is taking. When we go to the steady state or critical state data, these are typical results. These are two samples with the same void ratio but different initial confining pressure. This is one sample with 1 kilogram square centimeter, and this is with 5. These two have the same void ratio after consolidation, so both go to the same ending point, or the critical state or steady state, but there are some minimum strengths in this sample that is different than what we expect at large deformation. So here we have the critical state, and here we have this minimum condition of strength. Castro did this test also using a low control test, and in this particular case, he got, after 50 minutes of dead weight, this peak, and then the sample suddenly deformed significantly up to here. Okay, so there is a minimum strength, and if we don't apply more load, the sample stays stable here, although it passes through this minimum condition. And then he had to apply, again, dead weight on the sample in order to reach the steady state strength. So clearly we have two conditions. One is the steady state condition at large deformation, and one minimum strength condition. So that was the question to Jorge. And according to you, your opinion is we should use the minimum strength in the field, but trying to reproduce what is going on in the field. But this is, I'm working in a real project. I'm not working in the university. I'm just a practitioner. And we have significant problem when we are dealing with the stability analysis of tailing dam, because some people want to use this strength, some others are saying that we should use this strength. Yeah, and you have absolutely different results. Also, during the minimum strength, the sample deformed only in 10 seconds in this particular case. Okay, the name of quasi-steady state was proposed, as far as I understand, by Alarcón Guzmán doing this kind of test. Has a peak, a minimum strength, he called it quasi-steady state condition, and then the sample starts to dilate and increase the strength to the steady state strength. You will see the whole picture for the particular Toyota-san. This square, white square are the initial state, and the black dots are the steady state condition. And these are the quasi-steady state conditions. So we have two different lines. Of course, we can get this quasi-steady state only from very contractive sample. And in the case of a steady state, we can get this line from contractive state and also from dilative initial state.
And the problem is the quasi-steady state, as was mentioned also by Jorge, it's fabric dependent. So if we, in the lab, if we use two different methods of preparation, in this case we use wet tamping and also dry deposition, you have two different quasi-steady state lines, yeah, which depend on the initial fabric. These two tests, different initial fabric, but more or less similar or equal void ratio. So clearly, at the end, a large deformation, both reach same strengths and P, I mean mean stress. However, here at the initial of the test, we have quite different response. So the quasi-steady state clearly it's affected by the fabric. And in the case of tailings, very unfortunately, are significantly stratified. This is a tailings, real tailings. So when we test in the lab homogeneous soil sample with different fabric, this is just fabric to me, it's just orientation of particles. So these three samples should have same critical state line, okay? Because the initial fabric is completely erased, yeah, by large deformation. But when you have non-homogeneous soil samples with some layering inside, the large deformation will not erase this layering. So depending on the layering that we have, steady state line or critical state line will be different. These are results for San Fernando Sun. Clearly, there is a difference between the steady state line that you can obtain or critical state line that you get from remolded specimen, and these are results from undisturbed sample. Similar results, in this case of Tailings Sun, Cerro Negro in Chile. Remolded specimen give us this critical state line, and these are results from undisturbed sample. And the difference can be significant, as was presented this morning. Okay, so you may have these strengths, or you may have these other strengths, so depending on the fabric or structure of the soil. So the idea that we have, it's we have one steady state line or critical state line. Above that, we have contractive state, and below that, we have a dilative state. We can see some one consolidation isotropic line for the loosest state, and also we have a consolidation line for the densest state. So this is the whole framework where the soil can state. But we have this problem, or I see as a problem. Depending on the density and pressure, we may have a peak, this minimum strength, the quasi-steady state, and then finally the steady state strength. So what is the problem? Is that in this particular case, we start here. If we look the minimum strength, we are here to the left of the initial state. But if we look for the ultimate state or steady state strength, we are to the right. So doesn't mean that if you are above or below, you are getting only contraction or dilation. These are three cases. This particular data, point A, is below the steady state. The steady state in this case means large strain. And then you have a minimum strength, and then you reach the steady state. Okay, so point A, although it's below the critical state line, it has dilation. But for a while, it has a strong contraction. So it can contract significantly to a minimum strength, and then it dilates. In the case of point B, we are below, and we don't see here a significant reduction in strength, and it dilates because it's below the steady state line or critical state line. And point C is what we usually we expect usually. Okay, is below the below the critical state, so it dilates. So in this area, we have some cases where, although we are below the critical state, there is a strong contraction that generates this minimum strength. So we have here a zone where, starting below the steady state line, the material develop the quasi-steady state or a minimum strength that can be very, very different, significantly below. The strength can be significantly below than the ultimate state developed at large strain. And some people don't believe in the existence of the quasi-steady state, but different tests. This is a hollow cylindrical test, where the Yoshimine here was trying to identify the effect of the rotation of the mean stress. This is alpha, this is the angle of the main principal stress, sigma 1. And you see, depending on the value of alpha, you have different quasi-steady state, but the point is, there is a quasi-steady state, and it's quite different to take as a result, or as a strength of the material, this level or this level, okay? This level or that level. And actually, in all these cases, the strength still is increasing. So we don't know how much strength we can develop a really large deformation. So the point is, how can we deal with the quasi-steady state? So some people don't believe in it. I believe in it, and I think we should use it. But if you use it now as a critical state, or you consider that that is a critical state, there are two problems. It's fabric dependent, and also it developed just a limited deformation, okay? But maybe sufficient to create a failure. Okay, now I move to another topic, this instability line. Initially, Dobry presented this data. He showed that there is only one line, and if you cross it, the sample will collapse, or soil mass will collapse. So Sladen also present this idea, but he connect the steady state with the peak. What we observed that instability line exists, but it depends on the density of the material. We tested here for the loosest state that we are able to prepare sample in the lab, and we obtained this lower boundary for the instability line. So we just put took the peak, okay, to generate this line. So this is the lowest value, and this is the densest state that has just a very small drop in the strength. So this is the upper boundary. So depending on the density, you will have different instability lines that are in this region, from the loosest state to this densest state where you almost don't have a reduction in strength, okay? So instability line, it exists. However, it depends on the density of the material. This line is very important because it can explain failure. Like this one, this is a drain test. For example, there is a rise in the water table, so we move in terms of P to the left without changing the shear. So as far as you touch or you cross or you try to pass the collapse line, the sample will collapse or the soil mass will collapse. And also, this is very important. Usually, people run a strain control test. If you run a strain control test, you can pass this line and to reach the final steady strength. But if you run low control test in the drain condition, you are applying the weight slowly in order to dissipate all the pore pressure. As long as you pass this line, the sample will deform significantly, and you cannot control it because it's a low control. You have the weight inside, so the sample starts to deform because it's deforming too fast. You generate pore pressure, and the response of the material, it's undrained, and you will observe a collapse of the sample if it is loose enough. So people usually do drain tests in a strain control test and can reach, as I said before, the ending strengths in a drain condition. But under load control, you cannot do it. And now talk to a state parameter. Everyone knows the definition of state parameter, and it's a very wonderful idea and useful, definitely. Nevertheless, it has one limitation, according to my understanding, and that is that parameter doesn't take into account the static shear stress. So you have two samples with the same, here's three samples, okay, three conditions. This one, and this one, okay? These two samples don't have shear, static shear. They're isotropic consolidated. But this one, with the same state parameter, it has this level of shear, static shear. Although the three samples have same state parameter, these two will not collapse because they don't have initial shear. But this one, because it has static shear, will collapse because of that. So the state parameter is absolutely useful, however, it doesn't consider the static shear. So one possibility, probably there are many other, but one possibility is to add this, something we call it a flow state index. It's very simple, nothing special. It's just the minimum undrained strength divided by the static shear. Obviously, if the static shear is higher than the use, you have a failure. This is like a safety factors, nothing special. But the point is the static shear can be calculated by any analysis. Numerical analysis is very simple because it's force stresses. In general, to model a dam, for example, it's very complicated, the formation. It's very complicated to see how the pore pressure, variation of pore pressure. But under static condition, any simple model will give you reasonable values for the stresses. So it's very simple to evaluate the static stresses in a dam. And the problem is, of course, to calculate the minimum undrained strength. And that can be used CPT or whatever, or what people are normally using. So with this, immediately you know whether you are in trouble or not, okay? Because this is just available strengths comparing with static shear, okay? That now is a matter whether it will be triggered or not. So as a concluding remarks, under undrained load condition, laboratory test results show the existence of a singular state where sandy soil mobilized a minimum strength, developing a quite significant deformation, which has been called quasi-steady state. Experimental evidence indicates that the critical state line is not affected by the initial soil fabric. However, minimum strength condition is affected by soil fabric. That is the problem. In practice, it's not well defined whether to use the ultimate condition developed at large strength or the quasi-steady state condition if it is a riser. This is very important. In practical, when we are dealing with analysis and you have a reviewer, or I am a reviewer, it's absolutely complicated to agree whether the guy that using the minimum strength or another guy using the final ultimate state. So if the engineer, I would say, it's very conservative, will go immediately to the quasi-steady state. Immediately, and the guy will really fight because that is the strength. And if the guy is, let's say, brave or has a lot of experience and his judgment allow him to say, no, I will use critical state at large deformation, these are absolutely different results, and it's very, very difficult to convince people whether they are in this size or in the other. That's in my particular experience. The state parameter presents an important limitation since it doesn't incorporate the static shear in the initial stress state. One possibility for improvement is to also consider the ratio between the static shear and the minimum undrained strength. That's it. Thank you very much for your attention.
Thank you very much for a terrific presentation. You were also really on time. So we have time for questions and discussion. We start here. We already have some questions from online attendees, but do you have some questions here first? Yes, I can give you the microphone.
So you should come, the other speaker.
Thank you for this interesting topics presented today from all the speakers. I want to ask Professor Hicks about the reducing the uncertainty and the numerical modeling. Is there any developed or validated anisotropic critical state model that can be used for soil in general or for tailings in particular?
Anisotropic model for tailings.
Yep.
I'm afraid I wouldn't know. I wouldn't know the answer to that. I think as I haven't specifically looked at tailings myself. So all I've been involved with is the anisotropic model for sands.
Other question? Yeah.
I have a comment more than a question because I think Dr. Verdugo is looking for other opinions, and in the interest of this being a workshop. To me, the quasi-steady state or phase transformation is something that's occurring within a fairly narrow band of state parameters, something between 0 and minus 0.05 or minus 0.06, just marginally dense. And to answer your question about is it right to use that value versus at the field scale versus the steady state, I think, to me, it's really quite compelling and well laid out in Mike's book, where he shows the residual strength plots for what the drain strength is versus the quasi-steady state strength envelope, but then overlays case histories and a best practice line, which clearly shows that if you look at case histories where failures have occurred at the field scale, it's much closer to that minimum strength from a back calculation than it is to a critical state strength. I think it's quite dangerous in that zone to try and rely on the steady state, because for that to occur, you're really counting on that dilation to continue, where at the field scale, when things are really starting to happen, water's rushing in, in response to that initial tendency to dilate after the quasi-steady state, and it's just, you can't rely on it. And I think I'm getting to the microphone first before Mike can correct me, but our practice is if you're in that 0 to minus 0.05 range, you absolutely have to rely on that minimum as opposed to trying to use or to hope that you're going to dilate right to the steady state in that situation.
And as expected, here am I. First comment on the, I've got a comment and a question. The first comment is to Ramon, and more generally, it's a mea culpa to all of you. When we first proposed a state parameter, the context was we were building offshore platforms in a great hurry. And we were very much looking to the US Corps of Engineers, what they did back in the 1930s. So we went with the steady state school or the must dilate school. And we had a lot of data and we plotted up. And we just plotted up against the initial void ratio in the Traxel test, because that was, with massive database, and that was very convenient to do. Straight consulting practice. The mea culpa is when you actually put the mathematics together, you shouldn't be using the initial void ratio. You've got to use the void ratio at peak strength or the void ratio maximum dilatancy. And that's what you pick up, and that's what picks up the initial shear stress, because if you allow for the fact, as you put the shear stress on those samples that start for a Q of 0, the state parameter will change, and that picks up the effect of static shear stress. The mathematics are clean. You've got to use the state parameter as a moving variable not the initial variable at the beginning of the lab test. My question for the guys, the finite element merchants, when we ran the back analysis of Tar Island, as usual, we looked at the plasticity parameters and the latency parameters and yappity yap. But the thing that floored us was when we looked at the effective Gmax on the propagation of the failure. If we went with a fairly soft Gmax, we got a simple rotational failure, holding the same state parameter, the same plasticity parameters, the same hardening parameters. When we pushed Gmax towards its geophysical maximum, the whole failure mechanism changed from a simple rotational failure to this massive propagation outwards from 200 meters from a 12-meter high slope. So that literally the mechanism changed. My question to you guys, have you investigated the effect of elasticity parameters on your analyses?
You mean was a question for Hans Petter? or
well, for both of them.
Both of them, okay. Yeah. Michael, Hicks, and Hans.
Yeah, I haven't, but I guess.
One thing I can say there is, of course, if you go into softening, I call it softening or reduction in the strength due to contraction, you end up that you are localizing the deformation. And at the same time, you have elastic unloading on the other side. So it's a kind of balance there, because still you need to have compatibility in the deformation. So of course, if you make the elastic stiffness higher, you end up that affects in a way the global behavior, because these need to interact. So it's clearly that if you go into softening, that it is not only the brittleness of the curve that is plastic that matter, also the elastic part affects in a way the behavior, because it is the interaction between the zone that is elastically unloading and the part that is still plastically loading. So there this elastic stiffness comes in. Maybe one answer on this. But to go all the way to, as you say, that what is the consequence of it, that is a little bit more difficult. But you can study it numerically by having a parametric study of changing the elastic stiffness.
Yeah, that's certainly what we found when we were playing with it. The whole mechanism changed because the interplay between plasticity and because basically you've got to dump when you go over the top of a stress strain curve, you've got to dump that load somewhere else. Mm-hmm. And you then deal with the propagation velocity. And we have never seen anybody else publish anything like it, but we've got the complete change of mechanism, nothing to do with void ratio, just from this propagation velocity. And it shook us. And I then say, okay, guys, if we're interested in this, we need to look at Gmax a lot more. And then it's whether we got Gmax in the lab versus Gmax in situ. So I say Gmax is very much a player. It's my take.
Yeah. Your comment, the void ratio that it's here is after the static shear. It's considering the static shear. Because state parameter, the state parameter is defined in the EP, void ratio, mean stress. So there is no way in that plane to see the static shear.
But here I'm really sorry, but I need to use the flag of convener, and I need to say that take advantage of the coffee break that is coming soon. I also do have some questions from online audience, so okay. It's worth to take these questions and not to make them angry, because we don't consider them. Yeah. So I read the first question, which is actually for Professor Michael Hicks: how to incorporate measurement or observational uncertainties into the probabilistic analysis of slopes?
The sort of thing we do is use Kalman filtering techniques, for example. So, we've looked at taking pore pressure we've done one example where we've looked at, for example, the stability of a dike, and then use pore pressure measurements to update the analyses. But it's things like Kalman filtering, that type of thing.
Then there is another question, I think always related to your presentation. On slide 12, this is very precise, you mentioned that you were using Monte Carlo methods, but this person was not quite grasping the details of the approach. If you can just briefly comment on that.
Well, essentially what we're doing is we're, based upon, if we just, for example, think about the uncertainty in the material properties, our material property is defined by probability distribution and by some correlation scales as well. And using those statistics, we can generate a numerical prediction of the spatial variability at the site. But then what we can do is we can take the same statistics and we can generate another prediction at the site, and it will look very similar because it will be based on exactly the same set of statistics, but it won't be exactly the same with respect to the distribution of the strong and the weak zones. And so we can do that lots and lots of times, and for each realization, we will get a different solution when we plug it into a finite element analysis.
And there is another related question. Could you please clarify whether you create multiple soil models and then conduct slope stability analysis?
We conduct multiple realizations of the spatial variability.
Picking this from this
yes,
field.
But we will use the same constitutive model, you know, but we will be, if for example, we may, for example, like in this earthquake analyses, we were using a single model calibration, but we were generating random fields of void ratio. And so obviously, because we have spatial variability of the void ratio, we will have a spatial variation in the response across the domain.
And then there is a question for Ramon Verdugo. Where can we access experimental data showing the collapse of a load-controlled triaxial test loaded along a conventional stress path upon reaching the instability line? Where we can get the access to experimental data showing that?
I don't know. The data, he's talking about the data of Castro, I think, with load. The data are in his thesis. Very old one, but this one, probably. He's talking about those data, load control test.
Yeah, exactly.
Yeah.
Yes.
It's Castro, 1969, Harvard.
Great, thank you very much. I think we can, yeah, my last question.
Very quick comment. Ramon, on your point on the state parameter, and that could be for a discussion in the coffee break. I think even though you have the same state parameter over there,
It's public domain, it can be downloaded.
Yeah. I think even though you have the same state parameter, the latency state parameter, which is fabric dependent, is going to be different. So I think that is what would be explaining that. So ultimately, thank you. So all I was saying is that even though you have the same state parameter, I think that the latency state parameter, which is fabric dependent, is going to be different for the anisotropic test you have over there. So you can start from the same initial, I would say the same initial conditions, but I think you can see that differences.
Yeah, but the state parameter by itself is not enough. That's my point.
Yeah, it has to be modified by fabric for capturing
that, I believe. Yeah, there are many things to do, yeah. But alone is not enough. That's my point.
Okay.
Mike, do you want to quickly say this, the thing that you were mentioning before about the data?
Yeah, just responding to the discusser who's sort of emailed in or sent a comment in for looking for data. Everything, all the tests which are presented in my book, the data is public domain. So, and there are some load control tests. If you want to have a play with load control triaxial testing, plot up a stress strain curve in Excel, the data is widely on the internet. You just download it from the book, and there's, I don't know, maybe 10 load control tests. We gave up on because you get a cleaner response with displacement control, but there's some load control ones to play with. Free download.
Oh, thank you.
I think we can stop here. We can have a break and we can keep discussing. And there is one more question that I will save it and I will pose it to the audience tomorrow in the last a session of the day where we're going to have kind of open discussion. Thank you very much, and we are going to reconvene in 30 minutes. we can start. I think we can start this last session of the day. Just waiting a few minutes that everybody is taking a seat. Yes, so we can start with this last session of the day, and this session is about runout modeling and seismic design. Also in this session, we are going to have 3 speakers, and we are going to follow the same method. So first 3 presentations, and then we are going to have some questions at the very end. We start with Professor Scott McDougall from University of British Columbia, Canada, and he's assistant professor at UBC, known for geohazard expertise, including tailings dam breaches and innovative field data collection techniques. The floor is yours.
Great, thanks, Luca. Yeah, as Luca said, my name's Scott. I'm an associate professor at the University of British Columbia in Vancouver, Canada. Fighting about 9 hours of jet lag right now that kicked in just before my talk, unfortunately. But I'm here actually representing a pretty large project team, and I'll introduce you to them in a few slides. I think, and thanks to NGI and everyone for having us here today and giving us a chance to talk about this work. I think the flavor of this presentation is it's not a lecture, it's a little bit more of a show and tell. So I'll kind of go rapid fire through the work that all of the students have been leading on this CanBreach project. And I think also, I was asked to talk about runout modeling. That's a component of this work, but I'll also be talking about a bunch of other research that's closely connected with that in terms of consequences of tailings dam failures. So the purpose of the talk here really is just to give a broad overview of the project that we've been working on for the last 4 years and highlight some of the key outcomes. I'll talk first about the motivation for the project and introduce you to the project team and how it was structured. And then just quickly go through a summary of the key project outcomes, again, in terms of the individual projects that were led by the graduate students who were involved. So first, just at a high level, introducing the project itself. In terms of motivation, I don't want to belabor this point at all. I think if you're at this workshop, you understand this point here that tailing storage facilities can fail. And that means that standards and guidelines around the world have established guidelines for going about analyzing the potential runout of a tailings dam breach. And the goal of those kinds of analyses is to come up with inundation maps that can be used for things like emergency response planning. They also inform, in many cases, the dam design criteria themselves. So in terms of understanding the consequences of a tailings dam failure, very important to then understand how stringent the design criteria needs to be. And my own personal motivation, so I've been at the University of British Columbia for 7 years now doing research and teaching. Before starting at UBC full-time, I was a consulting engineer with BGC Engineering in Vancouver, and I was involved in a lot of these tailings dam breach analysis projects myself, and actually pretty frustrated with the tools that were available for me to do those analyses at the time. A lot of the methods that we used to look at the breaching of material through a dam were based on methods that had been established for water dam failures, not for tailings dam failures. So making adjustments to the analysis results based on those limited methods was very tricky. And then in terms of the runout downstream of the tailings storage facility after failure, a lot of the methods were either based on routing models for pure water flood routing, or models that were specifically designed for landslide runout. So at the far other end of the spectrum in terms of the solid content of the material. And the reality is that tailings flows kind of, there's a wide variety, but they tend to fall somewhere on the spectrum in between those two end members, between clear water floods and landslides. And so the two overall goals of the CanBreach project, and this goes back to, and I should say, the name CanBreach stands for Canadian Tailings Dam Breach Research, but it also has the double meaning, tailings dams can fail. And our two overall goals, and this is going back 4 years now, so we've been working on this for the past 4 years, and things have evolved since then, but our two overall goals when we started were first to significantly improve our understanding of the processes that are involved. So going back to case studies and really scrutinizing case studies and seeing what we could learn. Also running lab experiments and seeing fundamentally what's going on when a dam breaches. And then really important, again, getting back to the limitations that practitioners face was to try to come up with improvements to the tools and techniques that are actually used to try to improve the credibility of the inundation maps that practitioners are actually creating, which in turn improves the credibility of the dam consequence classifications and the emergency response plans. So it's a pretty large project team, sort of collaboration between 3 universities. So at the University of British Columbia, mainly taking the lead on the numerical modeling aspects of the project. Steve Evans at the University of Waterloo has been sort of in charge of the field and remote observations part of the work. And then our other collaborator, Andy Take at Queen's University in Kingston, Ontario, has been running physical model tests. And all this work has been supported by a team of industry collaborators, not just sponsors, but the way that the project is structured, they're actually involved in the research. NSERC, which is the funding agency in Canada, provides matching funds. So if industry partners put money into a research project, NSERC will match those funds. In this case, they also match the in-kind contributions of the industry partners. So the time that the industry partners were putting into the collaboration, in many cases, one-on-one with the students themselves, was also matched in terms of funding for the work. So the partners were Imperial Oil and Suncor Energy, 2 mine owners in Western Canada, and BGC, Clone, Cripp and Berger, and WSP, formerly Golder, 3 consulting engineering companies. And in terms of just the unique things that we could do with this research project, there's a large flume that Andy Take has been using at Queen's University for a long time, looking at things like landslide runout and waves generated by landslides into reservoirs. And there was an opportunity to retrofit this 36-meter long flume and actually create dams that we could then fail in the lab. So I'll talk about that in more detail a little bit later. All of the work's been led by the graduate students themselves, and the project's trained 18 students in total so far, if you include the undergraduate interns that have been shoveling sand in the flume in Kingston and working with numerical models at the University of British Columbia. And I kind of wanted to stay on this slide for a minute or so you could put faces to the young researchers kind of leading this work, because I think on the research side, we focus on the technical outcomes in terms of journal papers and the actual productivity of the research. But with projects like this, we're also training the next generation of tailings engineers in Canada. And all of these, the graduate students, most of the graduate students have completed their degrees and they've gone on to work for top companies now. So I'd like to highlight them for sure. So now I'll just kind of go through one at a time through the sub-projects, part of this larger project, and some of the key outcomes of that work. And just before I go through them, here's a list of the main things I want to highlight. We've developed some new accessible case history databases, so that's all open access stuff that we put out in the community. New insights into failure statistics, and I know there's some parallel work that's been going on at NGI as well on that front, as well as understanding capabilities and limitations of INSAR in terms of advanced warning. And then on the runout modeling, inundation estimation side of things, we've developed new empirical relationships that can be used for high-level inundation studies. We've also looked at capabilities and limitations of a series of numerical models that practitioners are actually using right now, and done as close as we can to an apples-to-apples comparison of those models using case history analyses. Through that work, we've got a better understanding of the sensitivities of the numerical models and in terms of how much effort a practitioner may need to put into different input parameters that go into those analyses. And in the lab experiment work, we've developed a better understanding of how the unique geometry of tailings dams and also the failure mechanisms may influence what the outflow hydrographs look like in the event of a breach. In terms of developing a database of case histories, this work has been led by Nayan Rana at the University of Waterloo. He's now a full-time engineer at Klonkrip and Berger. And one of the key things, the key principles of this work was to go back and actually really scrutinize the databases that had already been established. There's several, and I know NGI's worked with some of those data sets as well. We had concerns about the consistency of the terminology that was used and how reliable the mapping was in some of those data sets. So Nayan and other students who were supporting Nayan have actually gone back and looked at the case studies, first developing consistent definitions for things like runout distance and inundation area, and then reanalyzing the case studies in detail using the best available imagery and data to remeasure some of those parameters so that we had a lot more confidence in the database when we were then using it to come up with things like empirical relationships or using some of the detailed case studies to take those further to numerical modeling. So that database is open access and it's described in a paper that Nayan published in 2021. And yeah, a series of empirical relationships are sort of analyzed at a high level. And I know, again, similar work done in parallel here at NGI. Nayan also used that data set to go and look at the failure rates of tailings storage facilities. And I think one of the unique things with this analysis was, again, not just using the publicly available records, but making interpolations and extrapolations of the actual number of tailings storage facilities worldwide. And we know that a lot of those facilities are not reported. And so Nayan used some unique methods to try to correlate mineral production volumes with the number of tailings storage facilities, and that enabled kind of an estimate of the range of failure rates that are actually occurring. Nayan also compared that, the rates of tailings storage facility failures with the rates of large reservoir failures, so pure water dam failures, and they sort of fall in the same order of magnitude, and you can see that on the chart here in terms of failure rates since 1965. But you know, although the rates are comparable, the extent and environmental impact associated with tailings storage facilities has increased with the rising global rate of tailings production. We know these facilities are getting larger and larger over time, so the consequences of failure in many cases are getting higher. Nayan also, so originally part of Nayan's scope of work was to do some field investigations at sites that had experienced failures. And because of COVID, we were locked down and we couldn't actually do that field work. So instead, he pivoted and looked at remote sensing applications. And one application is obviously INSAR, and I know others are looking into that. I think we'll hear more about some of that other work tomorrow morning. And there were two aspects to this work. One, we had ground monitoring at a site where we could actually do ground truthing of INSAR back analysis of the monitoring data, and we found actually good correspondence between the ground measurements and the INSAR measurements, and that's probably not a big surprise. But when we tried to look at 7 case studies that had failed and see how well the INSAR monitoring could have predicted those failures in advance, we found that it was pretty limited in terms of being able to detect precursory accelerations. So that's probably not a surprise too, and also related to the frequency of that data collection in terms of the orbit times of the satellites. Now, in terms of runout analyses, the base that we collected allowed us to re-look at things like correlations between the volume of failure and the area of inundation. Again, going back to sort of the basics by defining what we mean by impact area. We developed this Zone 1 classification. So this is more or less the direct physical impacts of a tailings dam breach, the main solid tailings deposit, and correlating that with the outflow volumes. And we found this kind of highly scattered, but there is a correlation between the area and between the volume of failure and the area of inundation. And although there's a lot of scattering, I was nervous about showing this plot after Jorge's talk this morning. Like, look, I did a regression. This kind of thing actually is pretty useful from a high-level standpoint. And we know that because there's been previous correlations between area and volume for other types of mass movements. And you can see where the tailings flows plot on that, on the plot on the right, compared to those other types of failures. So it contextualizes tailings flows, in terms of their relative mobility compared to other types of landslides. And it also it gives us another way of cross-checking maybe more detailed analyses that would be done with numerical models. There was a student in the UBC mining department who kind of took that to another step by looking at combining that with estimates of cross-sectional area of inundation and including planimetric and cross-sectional area of inundation. She recalibrated the existing GIS model Lahar-Z, which is developed by the US Geological Survey to map Lahar, or volcanic debris flow hazards around their volcanoes. And she's recalibrated it with the tailings flow data and coded a new model that can be used for high-level inundation style analyses. So this is, again, appropriate in high-level applications. Sally's reason for doing this work was actually to look at, she was looking for a really fast method that could estimate inundation areas for a large number of tailings storage facilities. So in terms of understanding risk profiles for portfolios of facilities. But I think it can also be used as a cross-check on detailed numerical analyses. In terms of numerical models, because we were working with industry partners who all had their favorite in-house or commercial models that they like to work with, instead of focusing on the development of one specific model for tailings flows, we looked at a broad range of models. So you can see this is the Maris-Pruitt tailings storage facility failure back analyzed with 4 different numerical models. And visually, you can see some differences there. They've all been calibrated to try to match the inundation area as well as arrival time estimates at the distal end. And all of them were reasonably capable of reproducing those bulk observations. But the input parameters that were needed in each of those models to do that were different for the different models. So understanding that input parameters are not necessarily transferable between different models, I think that's important for practitioners to know. Probably not a big surprise, though. And it also gave us a chance to understand some of the capabilities and limitations of the specific models. The other thing that came out of this work was that the input parameters that were needed to match those events didn't necessarily match with independently measured properties of real tailings. And this is just showing 2 plots. One's yield stress on the left and the other's dynamic viscosity on the right. And you can see, especially on the right in terms of dynamic viscosity, we're like off the charts where the numerical models are. It's kind of uncharted territory in terms of the measured rheological properties of those tailings materials. And maybe not surprising because tailings flows will incorporate the dam materials as well as materials downstream. So just measuring the properties of the tailings themselves doesn't tell you everything you need to know to run a numerical model for Runout. I had a master's student, Daniel Adria, who took that work to the next step, trying to compile really detailed information for a collection of case studies. So this took actually a lot longer than we were expecting. And really, I think his big contribution is this new database that can be used by other numerical modelers using different numerical models. And I think we'll hear about Bingclaw in a couple of talks, but it's a data set with really detailed observations of arrival times, velocities, inundation areas for a collection of 12 case studies. And that work is in review, and hopefully the peer reviewers will see the value in that. But when the case study database is available, I'm hoping that people will try to use it with different numerical models and see what they come up with. For Daniel's work, he was using the numerical model HEC-RAS, and he came up with a systematic way of calibrating that model to determine the best fit input parameters for all of the events in his data set. One of the things he found, maybe not surprisingly, that the quality of the digital elevation models that go into those runout analyses really strongly influence the results. So Daniel will tell you that you get what you pay for in terms of the quality of the DEMs that you may be purchasing for these types of analyses. And then in collaboration with one of my PhD students, Nagar Garamani, who's just graduated recently and gone on, she's working at WSP now, they used those 12 case studies to look at the sensitivity of the model results to different ranges of input parameters. So estimates were made of around uncertainty of the input parameters, and then they looked at how that affected the runout results. Probably not surprisingly, inundation area was very sensitive to the volume of failure, so that's consistent with what we found with the empirical analyses. But the rheological input parameter values also had a big influence on the simulated velocities and arrival times along the path. Nagar also explored ways of using this information probabilistically, so taking uncertainty in the input parameters and trying to use the probability distributions around that in a Monte Carlo style analyses to look at probability of a range of probabilities of runout. And I'm not sure if practitioners are ready for this style of analysis just yet, but it was an interesting demonstration of what can be done with these models in terms of probabilistic estimates. And then in parallel with all this other work that I've been describing at Queen's University, Kaylee Barlow was a master's student who was exploring the use of the model XBeach for simulating the actual breach process for these types of events. XBeach is a model that was developed for looking at breaches of barrier islands in coastal engineering applications. But we saw some similarities with what we were trying to simulate in the lab there with these small sand dams. And it looks like XBeach is a promising tool for these kinds of analyses. So giving practitioners another tool in the toolbox for trying to estimate the breach outflow hydrographs, which then become input to the runout models. In terms of the lab experiments themselves that were being run at Queen's University, Andrea Walsh was running just simple notch overtopping experiments, but modifying the dam geometry to look a little bit more like a tailings facility. So we're experimenting with pretty simple uniform sand, but then seeing how things like the upstream slope of the dam, how that might affect the peak discharge or the time to peak discharge. And Andrea found that there was actually good analytical solution that was available that matched the lab data fairly well, and also that higher peak discharges were associated with steeper upstream slope angles. So looking at that another way, if you have a relatively flat sloping tailings beach upstream of a dam, there's a good chance that it could attenuate the peak discharges. And taking that a step further, looking at different depths to the beach on the upstream side of the dam, Andrea ran some other experiments just looking at sensitivity to that tailing-specific geometry. And she found that above a threshold beach height, the peak outflow was limited by the geometry of the reservoir upstream. And this is something we're trying to explore a little bit more, trying to understand how much the volume of that reservoir upstream influences these measured peak discharges in the lab. Now, Megan McKellar is a PhD student who's just trying to finish up her research this year, and she's been running lab experiments, sort of expanding the number of failure mechanisms that we can investigate in the lab. So moving from the simple notch overtopping experiments to, in this case, a seepage failure experiment. You can see the evolution of the failure there and eventually the overtopping that, that leads to the catastrophic breach. And this is just another view. So in these experiments, she's colored the sand upstream so that you can see this ellipse shape developing. You can see some effect of the flume sidewalls there as well. And one of the surprising things was that in all of these different failure mechanisms scenarios, so the third one that she looked at was like a broad overtopping, something similar to like a landslide generated wave, maybe, or a long period wave of some sort overtopping the dam and initiating catastrophic overflow. The peak discharge was the same in all, more or less the same in all of those failure cases. The only difference was the time to the peak discharge. So understanding why that's the case, that's an open question for us right now too. Megan's moving on to look at sudden release of material using this guillotine gate system that she's developed, and that'll hopefully trigger liquefaction, and we can look at some flow slide analogies as well. And I think the students have made some good advancements in collaboration with the industry partners over the last 4 years. There's obviously many other questions that have been raised through this work, and I think the need for further research in 3 main areas has been identified. We'd like to start experimenting with real tailings or tailings-like materials, and I know Paul Sims at Carleton University in Canada has started down that path using Lita clay as an analog for fine tailings. We need to link the numerical modeling with the lab experiments and tests a lot better, so we'll be looking at back analyzing the experimental data using different numerical models, and then investigating field behavior and geomorphic analogs. So we know there's similarities with quick clay landslides, natural landslide dam breaches, and so we'll be investigating that as well. All the papers that I mentioned in the bottom corner of each of the slides and the open access databases that I mentioned are available at our website, canbreach.ca, so you can check out that site for links to those references. And otherwise, thanks. Look forward to discussion over the next couple of days.
Thank you very much for your very comprehensive presentation about all the things going on in your research group. We move on with the next speaker, and the next one is Professor Deepankar Chaudhary. I hope I have not mispronounced your name. And he's from IIT Bombay, India. He's head of the civil engineering at IIT Bombay, specializing in earthquake-resistant geotechnical structures and seismic design of Indian tailings dam. Please, the floor is yours.
Good afternoon, everyone. And also, I welcome all the participants who are attending online. Good day to all of you. Thanks to NGI, Sparsha, Dominik for the invitation to have me here. So today I'm going to talk about seismic design of tailing dams. I'm going to focus on Indian case study. I understand that my name probably is a bit difficult to pronounce, but for geotechnical engineers, it is not a problem. I say you can call me as Deep Anchor, because anchor everyone knows in geotech, and though I work in shallow anchor, but my name is Deep Anchor. Okay, anyway, so moving forward, I must acknowledge the work which I'm going to present today to my former students who have worked on this project, Dr. Debargha Chakrabarty, who is currently Associate Professor at IIT Kharagpur. Those of you know about IIT system, probably we have glorious alumnus of IIT Kharagpur, CEO of Google, US. Then Dr. Sanjay Nimbalkar, who did PhD with me and worked on this project, which I am talking today. Currently, he is associate professor at UTS Sydney in Australia. And another, my former PhD scholar, Dr. Jayakumar Shukla, who is in industry and entrepreneur. He is having his own company, Geodynamics, which is, you can say, the Pile Dynamics US, their Indian part. Of course, we know the need of research on earthquake engineering. This is my basic area of research, geotechnical earthquake engineering. When I was discussing with Sparsha about the selection of the topic in this tailing dam workshop, and since morning we have heard fantastic lectures on various aspects. So she said probably the seismic aspect is not covered, and coming from this geotechnical earthquake engineering, I said, okay, that will be really my pleasure to talk something about this. And this statistics clearly shows in last entire century, 20th century, if you see the statistics, the earthquake takes the majority of the share of all the disasters worldwide. And if we talk about the region-specific disaster, probably Asia and Pacific region takes the majority. And that way, I will say this part of Europe, the Norway is blessed not to have too much of earthquake disaster, but probably Italy and Greece is not so blessed. Anyway, so in the introduction, we all know about how the difficult situation can happen. We have seen the static failures of tailing dams since morning, several case studies, problems, lab tests, numerical modeling, everything. So you can imagine that the problem becomes manifold when earthquake or such kind of dynamic forces gets added to it. So essentially, coming to the classification of tailing dam, we generally classify into two types, either water retention type or raised embankment type, within which, based on the construction methodology, we can have upstream method of construction, downstream method, or centerline method of construction. I take this statistics published by ICOLD in 2001, which says clearly, if you look at over here, the majority factor of the number of incidents of failure is actually second highest is the earthquake after the slope stability failure. So essentially, if we really want to make our tailing dams also safe, these are the two factors probably we need to look very carefully, and accordingly we should analyze. In literature, you will find several analysis on such method, starting from the classical numeric sliding block method, followed by a Magdisi-Seed method, and there are advanced model by Radje, Bray, Wartman, and many others. So this is a background of the tailing dam incident during the earthquake, how a failure of a tailing dam can be animated through this. One can see over here. These are few statistics of landslide dams, which actually Professor Limin Zhang, he has shared this data. You see the majority of the failures comes in China, followed by several other countries. And as I have already mentioned, one of the major factor is earthquake, on which I'm talking about today. These are various methods in the literature you will find for such tailing dam stability analysis. One is the classical old theory of pseudostatic method of analysis, where somebody can apply the popular method started in 1920s till 1960s. I will say this was very much popular and used in practice. Even today also people do use it, but there are various limitations of that method. I will talk about that very shortly. Sliding block method also we know about. Numeric sliding block method is the basic one. Then several advancement has taken place on that. Then we have shear beam model, starting with Mononobe's first introduced one-dimensional shear beam model, and further several researchers, including Professor George Gazettas, actually have improved on this shear beam model concept. We have also seen several analyses this morning how finite element method can be used, or finite difference method. There are several research works one can see. Many analytical methods also came up where people tried to give the closed from design solution. One of our group, as I mentioned, my first PhD scholar, Dr. Sanjay Nimbalkar, who is in Australia now. So we actually developed the amplification-based pseudostatic method of tailing dam stability analysis, which briefly I will talk about in this presentation also. Several software packages for the numerical analysis. We have seen today speakers talking about the application of Plaxis. Today I will be talking about how the FLAC can be effectively used for such analysis, and also the centrifuge modeling or the 1G lab test, as my previous speaker also has mentioned about it. If we see the codal provisions, what are the various countries' code talk about? As I'm representing today the Indian case studies and how we do the design, I'll be sticking to the Indian code, what it says about. So we have exclusive IS code, Indian standard 7894, which talks about the tailing dam stability analysis. It essentially takes the conventional pseudostatic approach, as I have mentioned, that is most popular, where it mentions that we can find out the factor of safety using this equation, which is given over there. And for the seismic design, we have IS code 1893, which talks about how to consider the portion of the dam for the rupture analysis and so on. Coming to the field applications of our research finding, this is an actual field problem in India, for which at IIT Bombay we have actually were part of this project. It is a seismic design of the tailing dam in the eastern part of India, where the essential requirement of the material is to store non-radioactive nuclear waste material. As this project was given by the Department of Atomic Energy, and as per the IAEA standard and also our Atomic Energy Regulatory Board, what are the material to be stored and what height should be given, and there's seismic stability analysis we had carried out at IIT Bombay in our lab during 2006 to 2009. So this is the location of the site you see with the star. This is essentially the India's seismic zonation map. We have 4 different seismic zones. Zone 5 is the most severe earthquake hazardous area, which is the dark red color, followed by Zone 4, little less hazardous, which is in orange in color, followed by Zone 3, which is yellow in color. And among these 4, the least hazardous zone is the blue one, which is Zone 2 seismically. So this site is actually at seismic zone 2. Though it is at seismic zone 2, that is the selection of site, as you know, it should be always. But even then, there is some design acceleration, and for which we must design the such kind of structure accordingly. So this is the exact problem definition. If you look at, there are 2 sections over here. The smaller one is at the first stage. So this tailing is proposed to be constructed into 2 phases, depending on amount of the material which is going to be dumped over there. So in the phase 1 is this one, and the phase 2 is the bigger one over here. This is the cross-sectional view. You see, this is, as I already mentioned, is constructed at the least seismic hazardous zone in India, in the eastern part, seismic zone 2, as per our Indian standard seismic design code. And we have analyzed through FLAC 3D analysis, that is the finite difference method, and these are the properties. So this material property actually was supplied by our Bhabha Atomic Research Center, where they have studied the entire region and also the material to be dumped, and all those properties we actually got as an input parameter for our seismic design further. As I already mentioned, this is the 2-phase construction problem has been actually put forward. In the first phase of construction, these are various sectional areas you can see. First phase, the proposed height of tailing dam is 10 meters above the ground level. And in the second phase of construction, it will become 28 meters whenever the requirement of the storage material comes to that stage. If somebody is interested, you will get this. We have published in ASC Geotechnical Special Publication of 2011. So this is the FLAC 3-dimensional model generation analysis with both the static analysis first we have to satisfy and check whether it is safe or not, then forward to with the seismic analysis which has been done in this case. But remember, there are several cases of loading which need to be checked, because I saw in the morning half one speaker actually mentioned that though you get a factor of safety 2, but still the situation failed. And obviously that can be because of some other load cases, as we know. So these are the 7 load combinations or the cases actually as analyzed in the present problem. You can see what are the cases. The case 1 is when the water table is 3 meters below the existing ground level. The second condition is when the water table in the reservoir is up to the top surface of pond tailing portion. The third case is when the reservoir is filled with only water, that is no tailing material has been dumped, because you know the dumping sequence is essentially first to store water and then you dump the materials over there. When the pond tailing portion is filled with water, that is the fourth combination, then pond tailing portion is filled with a slurry, that is just you dump the material and it is completely in a slurry state. The sixth position is when the reservoir is filled with slurry only, and the seventh condition is when the reservoir is empty. So these all 7 load combinations have been considered, and as per UNEP guideline, the 42% of the solid content in the slurry density is obtained with this unit weight. Coming to the seismicity, when we come to the seismicity, this is another important point I want to mention over here, because there will be regulations, and also in software you will get the conventional seismic ground motions, which typically in the seismic design, if people are not fully from the geotechnical earthquake engineering area, they adopt those ground motions available in the software. So it is flooded with like Kobe motion, El Centro earthquake motion, Loma Prieta motion, all these well-known ground motions in the software. But we have to think about whether that type of ground motion is going to get created at your site or not. So until and unless the situation is actually that, and you prove it geotechnical way or geophysical way, otherwise the assumption of the ground motions available in the standard library of the software is not correct. So what needs to be done, also along with your standard library ground motions, you have to select the synthetic time history, multiple type of synthetic time history, which is commensurate or which will satisfy that geological condition or the site condition, take it from the bedrock to top, and then took it down, which call it convolution and deconvolution theorem, and apply and check whether your assumed synthetic time history is actually matching with your geotechnical profile and the strata, etc. So until and unless that matches, otherwise your assumed so-called seismic motion or ground motion is not correct to be considered. In this case, another important aspect, I think earlier there was an excellent discussion. He has asked about the use of the Gmax, because Gmax is probably the lab and field Gmax we know from even 2011 Tarzagi lecture by Kenneth Stokey. He clearly has shown from the data it can vary 2 to 4 times higher and lower in either side from the field test to lab test. Then which Gmax value has to be taken? When it comes to the dynamic analysis, things even become complicated. Why? Because you are no longer dealing with the strain range of static range, which is as a small strain problem, but these are earthquake-induced problems, which are highly large strain problem. When you deal with such large strain problem, there is a degradation of your G parameter, and hence you have to consider the reduced G parameter. And in the dynamic design, there is a standard thing we generally say that typically the E dynamic is 0.2 to 0.4 times of the E static. So essentially, how you relate your elastic components of those moduli in design concept of the dynamic by this reduction technique, and that has to be from the field test again, rather than mostly from the lab test. So this is one of the acceleration time history I'm showing though, but there are several such time history has been chosen for such design, and also the geological and local site effect based time histories has been taken care of. So after doing that, these are maximum displacement you can see under various seismic loading condition in different directions of positive X and positive Z and so on. For all the 7 cases, you see. This is for the first phase because we have to actually stabilize or prove to be stabilized both the phase 1 dam as well as phase 2 dam whenever the design requirement is come. So this is the publication which I was talking about. And here you have to check not only 2 aspects you have to check. This is the 30 seconds earthquake motion has been applied, which is suitable for the site. We have to check at the transient phase as well as the steady state phase. What is that? Essentially, you know, though in the transient phase, the value may be much higher, but essentially there will be a delay or lag in the failure, which essentially the phenomenon we see in the cyclic liquefaction also, that liquefaction triggering never happens along with the peak ground acceleration when it comes. It always have a time difference of about a couple of minutes to occur the peak liquefaction. The same thing has to be checked over here, whether the failure of the dam or the factor of safety reduction or the settlement is transient or at the steady state. At steady state also, what value it reaches, one need to check those things. So these are various analysis of the seismic part. You can see for both phase 1, the top one, and the second one is for the phase 2 of the dam has been done. This is one interesting thing. One should look at it because this only happens during the seismicity. What happens, as you know, when the seismic motion, what we give at the bedrock level first, bedrock to it comes to the ground level, and then it passes through your several layers of the whatever the tailing portions and whatever stored material is there, because of the non-compacted or just dumped or filled material of the tailing portion, there is a high chance actually those ground motions gets amplified, which we call as a seismic amplification. And it's a common phenomenon, like a classical example of a Mexico City 1985 earthquake is very well known for that, because people say the amplification was the main reason, not the bedrock level seismic acceleration. So this study clearly shows how much amplification is possible to occur at different depth and height. You can see over 3.93 times of the amplification, and which is quite acceptable, you know, because of the, I will say, the softness of the material or the loose state of the tailing material. So we need to check and certify, yes, under that high soil amplification also the stability will not be in danger. This is some comparison with the FLAC analysis. How do we know that our software, whatever is giving, is correct or not? Because many people say the software is garbage in and garbage out. So we have to prove that it is not so. So for that, we need to know the basics and steps, what goes in for the software analysis. So you see over here that the fundamental time period for the first phase and second phase of the dam that has been calculated, and also IS code gives us about the computation of time period, and which typically of the similar range. If you check the values 0.33 versus 0.3, 0.9 versus 0.83, so which actually tells about, okay, probably the analysis is correct. This is about the second phase of the dam analysis with both static and seismic phases. You see all the load cases have been considered, maximum displacement under gravity loading as well as the seismic loading. Also, not only the FLAC, we didn't depend on only one type of analysis or one type of software, I will say, but also the codal provision and the analytical process, and also different other software which takes care of different methods, because you know the FLAC takes care of finite difference method, whereas Plaxis, Taldrain, Slope W, these are essentially on finite element based. So there is a big difference between the two. So we have also checked how this factor of safety actually changes if you change your software or your analysis type. So these are various slope stability analysis results. You see the static factor of safety and the seismic factor of safety. These are for various input values. If you take care, because Taldrain and Slope W has their own limitations. What are the limitations? It cannot carry out the real dynamic analysis. It can do the equivalent static or the quasi-static or the pseudostatic analysis. Like you give some figures of equivalent acceleration like 0.1 g, 0.05 g in horizontal and vertical direction, and accordingly, equivalently, additional static load it analyzes for. So we have checked for those conditions also along with the dynamic analysis, which we will come later. So these are some of the seismic results you can see over here. Then I am referring to how we have carried out, as I said, the conventional pseudostatic method and the method which, the pseudodynamic method which Steedman and Zeng in 1990, first they introduced, and then my PhD scholar, Dr. Sanjay Nimbalkar has developed. We had a classical paper on this in Geotechnical in 2005. One can see this, how this pseudodynamic method has been actually formulated for the any stability analysis of geotechnical problem, considering the dynamic effect, not only the static effect. So what are the additional features compared to the pseudostatic analysis, which is equivalent static? So we only consider the horizontal and vertical seismic accelerations equivalent to a static additional forces, but that is not sufficient, as we know, because it neither considered the effect of the time, it doesn't consider the geological material property under the dynamic loading condition. No dynamic properties are considered, no shear wave velocity, no G value, nothing is considered. So all these things has actually eliminated in this new method of pseudodynamic model, where both the shear wave velocity and the primary wave velocity, essentially, which is the major basics of the earthquake engineering, because these values also can be taken care of in the analysis of the stability of such dam. So this is the pseudodynamic analysis. So we have divided into various segments, you can see, and this is also a time varying force, so that's why it is not a constant. It actually, from this level to this level, when it goes up, it is actually dependent on the depth, dependent on time, dependent on shear wave velocity, primary wave velocity, and so on. So this is how the factor of safety can be calculated using this pseudodynamic method. It looks complicated, but one can see our journal paper on that, because I understand that showing equations probably take half of the audience out. So this is how we actually try to formulate the closed form solution of the stability using the proposed pseudodynamic model, and accordingly, all the segments have been actually analyzed using this second phase and first phase, both for the pseudodynamic analysis. And you can see pseudodynamic analysis many a times give more critical value because it takes care of all the seismicity effect, time effect, shear wave velocity or the geotechnical material effect, and also the frequency content of the earthquake, which are the real dynamic effect need to be considered, which pseudostatic method cannot consider. Then another major factor, which many lectures we have seen since morning about talking about liquefaction, but mostly those are static liquefaction, as all the speakers have mentioned. I am focusing here only the cyclic liquefaction, the dynamic liquefaction. Due to earthquake, what liquefaction is going to possible to happen? Why liquefaction is going to happen cyclically? Because, again, coming back to the material, it is a loose state, mostly. It is completely in saturated condition. These two are the most favorable condition for the liquefaction to happen. So one need to check whether the cyclic liquefaction also is going to happen for the section or not. That we also have carried out. We have simulated in FLAC how the liquefaction scenario, and you can see the Brand model, essentially the 1991, the program can be written and called according to the material properties for the site. It is not that, again, whatever is available in the standard software model that can be used. It should be always site specific. One thing I must mention, it is our limitation actually. We have used the simple Moore Coulomb model. Since morning, we were really looking at several excellent characterization of the tailing dam materials, where even the critical state model and everything has been talked about. But what we found, there are two ways of doing it. Many people actually do a design considering the classical critical state and I will say more realistic complex constitutive model, which is perfectly fine. But there are, remember, about 10 to 15 parameters which need to be fed in your program if you're using that. On the vice versa, you have more Coulomb, which is a very simple model, deals with only C and phi. You need only 2 parameters, which is gross, and it will never give you a correct approach of using this. But how to balance these two? Because many times I have seen people are feeding those 10, 15 data of the strong constitutive model without doing the test or assuming the values. So whether assuming value, going for a complicated constitutive model is better for practical design, or using the lab test C5 value, realistic value, and going for a simple, more Coulomb model. So there can be a lot of debate, I understand, on this topic. So this is one of the limitations, I must say, in our work over here. Then we have calculated the liquefaction potential for this site, for both phase 1 and phase 2. You can see this is for phase 1. These are the locations essentially we have chosen because, close to the ground surface will be more prone for the liquefaction. So these are the points we need to check. And this is for the phase 2. You see, one of the most important parameter we need to check over here, the excess pore pressure ratio, which actually defines RU value. If it reaches 1, we say it's full liquefaction. But RU value reaches 0.9 and above, also we cannot say that it is safe against liquefaction, cyclic liquefaction, because it can be partial liquefaction also, as you know. So that's what you see our final value for this side. We obtained at this, and we certify that, yes, this is safe against liquefaction also. These are the detailed analysis for the cyclic liquefaction. You can see for various phases of the dam at various height and so on. So these are few findings, as I have already mentioned, that how much seismic loading adds to it in the realistic design for the second phase of the dam. And for the first phase, actually at present, the site condition is, as we have completed this project in 2009, so about 14 years ago. So this first phase construction is already completed. Second phase will be done when there is a requirement coming later on. And these are the various steps. What is the maximum factor of safety? What is the amplification to be checked? What is the liquefaction RU value, and all those things. So with this, I understand my time is over. So this is the concluding remarks. As the site is in Jadugoda, we try to make seismically the tailing dam safe for the site, which is in the seismic zone 2 in India. So thank you. And a quick comment, not related to the workshop, but we also publish Indian Geotechnical Journal by Springer. It is a 53 years old society journal. And recently, last year, we got impact factor in SCI also, 1.4. It is Scopus listed and all those things. I request all of you, whether you are in academia, in industry, please do submit your best quality original papers or case study, case histories, review papers over here. And probably I can say happily that I have requested Professor Suzanne Lacasse, and Professor Suzanne has kindly agreed to be in our editorial board as associate editor. So thank you so much, and look forward to interact with all of you. Thank you, and namaste.
Thank you very much for your great presentation. So we move forward with next speaker, and then if you can come back together with the other speaker here, we can have a small discussion. Next speaker is from NGI, is Chongchang Liu. Is a senior geotechnical engineer at NGI Oslo with expertise in risk assessment, statistical analysis, and numerical analysis, and is leading NGI's research group risk and reliability. Chongchang, the floor is yours.
Yes, thank you, Luca, for the nice introduction. I'm today presenting our work on risk assessment of the Tailings dam bridge. So, as you can see, this work is not done by myself, but it's in collaboration with with many NGI colleagues. I think many of them are sitting in the audience. If you have any questions, perhaps co-authors could take it. So basically, as we all know, this tailings dam over the past century, if we look at the figures on the bottom here, so we can see many catastrophic tailings dam and the resulting force flowing mud flow had led to a very very large damage and also cause a lot of deaths of people here. So we do have a few very big failure events here. So we have, for example, this very well-known Fengdao failure. So it released about, I think, over 30 million cubic meter of tailings material. And the well-known Feijiao tailings failure, they caused a lot of people died, and I think more than 270 people lost their life. So keeping the tailings storage facility safe is one of the big challenges we are facing in the mining industry and also tailings industry here. So as we all know, there are still a lot of active tailings storage in the world, and a lot of old or closed tailings facilities with unknown risk conditions. So to prevent this unexpected sudden failure, so we believe there's a need for comprehensive system for risk assessment and risk management of tailings dam here. This Professor Morgenstern also emphasized at one of his lectures. So we are facing a challenge here because of we are still lacking the technology, or we are still lacking the solution in our design and performance of tailings dam. And he also pointed out is a need to consider risk and reliability-based approach or framework for tailings dam risk assessment and failure. So the purpose of our study here is to integrate new methodologies and the methods to modeling the stability and the large deformation with models suitable for tailings material into a new risk assessment framework. In today's session, we have been listening a lot of new techniques, and we are improving our understanding of tailings material all the time. So this basically the risk assessment and management framework we proposed. Is a very busy figure here, but if you follow all these steps step by step, it's basically quite straightforward. We basically consider 4 components in this framework. So in the green zone, we need to collect all information for risk and hazard assessment. And in the yellow zone here, we conduct probabilistic analysis in terms of stability analysis and also dam breach analysis. And in the light blue zone here, we need to communicate risk and take risk-informed decisions. For instance, we need to implement measures if the tailings facility is unstable, and we need to reduce risk by taking into account of some measures here. And also different parties, we need to communicate risk with same language. And as we all know, tailings facility is different from regular water dams. It's rising all the time. So that's why we are saying risk assessment is not static for tailings facilities. So it's a dynamic process. So we need to consider all these factors even after closure. You know, that a sudden change in pore pressure could lead tailings failure. I think tomorrow our colleagues from Titania and Sweco, they will present a very nice case study where they look into performance of a tailings dam with time. So they have to take into account significant measure to stabilize the tailings dam facility. So today, because of a time limit, I cannot touch on all these components, but rather look into the components in the yellow zone. So talking about the probabilistic stability analysis and also dam breach and consequence analysis. So we have been talking about this behavior of tailings for quite a while, and we come up with different models and very advanced numerical solutions as well. So basically, we know that the tailings is it's very often is brittle material. So we have this progressive failure when we have large stream. So basically, if we know this behavior, we could consider advanced modeling to perform or carry out numerical modeling. But the difficulty for dam breach analysis, we normally ignore this process. We consider the residue, the yield strength in the post-failure analysis. And this process basically is quite important if we take into account the full picture here. And as our previous speakers were talking about, we have numerical solutions in terms of finite element analysis. We have advanced model to come up with the stability analysis of tailings material. We have both no sand model and sandy sand model to carry out our numerical simulations. The probabilistic analysis here I'm presenting is based on this behavior of tailings material, and also by using the finite element model, using the no sand model here. So the case study I want to present is basically an idealized tailings dam. So the tailings dam is 50 meters high. We have a vertical line here. So it's starting from the toe with the distance of 30 meters and end up with around the middle on this side. So basically our simulation is done by lifting the vertical line on this side. So we keep vertical line here as fixed. So basically, why we carry out a probabilistic analysis? The idea is that if we look at, we have 3 CPTs to be used to characterize our tailings material. So if we look at the state parameter interpreted from various CPT correlations, so we can say there is a very big scatter. So even with one method, so we end up with a large variation in the state parameter, and especially for the top layer, you can see the scatter is huge. But the nice thing is we have CPT measurement. The CPT is fascinating because it's continuous measurement, and we could come up with state parameters by using all these correlations here. But this just motivated us to carry out probabilistic analysis by considering all the uncertainties in this important parameter, state parameter here. And the method we used for our probabilistic stability analysis is response surface combined with first order and second order reliability method. As Professor Mike Hicks pointed out, they were using Monte Carlo simulations. But the difficulty here, we cannot use Monte Carlo simulations. Because as Hans-Peter mentioned in his presentation, the finite element analysis we carried out is basically, firstly, we have drained condition, and then we switch to undrained condition, and then we apply the gravity loading. But this process is not automatic process. So we have to switch from drained condition to undrained condition by hand. So that's why we couldn't use Monte Carlo simulation in this aspect. So we basically we want to use a response surface to approximate the behavior or the response of the tailings dam here. So the idea here is we have uncertainties in our tailings material. So in this case, is state parameter, interpreted from CPT correlations. And we don't have a geometry variation in this case study, but we do vary the theoretical line in this analysis. And then we carry out a couple of simulations, but not 100 or 1,000 simulations to come up with this response surface. But the number of simulations you carry out is really dependent on the numbers of random variables in your simulations. So basically, we end up with a response of this slope, given the uncertainties in the soil parameters or tailings parameters here. And then we end up with a second-order polynomial equation here. And then this is the performance function for us to further carry out probabilistic analysis by using the reliability method. I'm not going into details of all this reliability method, but we can discuss later on if you are interested. As I mentioned, the uncertainty is basically, we consider the uncertainties in the state parameters in 4 layers. So basically, as you know, the theoretical line, we have a unsaturated and saturated material. So basically, this layer 1 and 2 is unsaturated materials, and layer 3 and layer 4 are saturated materials. And if you remember, we have a big, very large scatter in layer 1. So basically, we don't really know if the material tailings in layer 1 is contractive or dilative. So we end up with a very large scatter. So basically, COA is 400% here. And then we have contractive loose materials in layers 3 and layer 4, layer 2 as well. But layer 3, layer 4 uncertainty is relatively low compared to layer 2. But basically, the simulation we carried out is that the static liquefaction is always taking place at the toe of the slope. So layer 3, layer 4, from deterministic analysis, we know is really important, the state parameter. And then if we look at the figure on the right hand, so that gave you a feeling of how probability of failure is changing by changing the theoretical line. So when we have a theoretical line at the location of 26 meters, we end up with a small probability of failure. When we lift the theoretical line to the top of the slope, the probability of failure is becoming very, very big. And then I cite the uncertainty of in state parameter, we could quantify from this pie chart as well. So it's not surprising the layer 3, layer 4, they are playing an important role in the performance of this slope. Then move on to the runout modeling. So this is the in-house software we developed that we are very proud of. We consider the Herschel-Berkeley rheology. So it's well known that tailings material is basically this Bingham rheology and the extension of Bingham Herschel-Berkeley rheology is suitable for tailings material. And we developed this model. So basically, we have one unit, and the line here basically is that the yield strength is equal to the shear stress. So basically, the plug layer is behaving like a solid. So it's floating above the shear layer here. And we consider time average model in 2 horizontal dimensions that enables us to carry out simulations without too much computational time. And basically, the shear layer is the key here. So if we vary the shear stress, basically we can determine the velocity and also the depth of shear layer as well. And this basically the equation for our binc law. software. So we have this the yield surface. We have a plug layer, and we have a shear layer here. The flow exponent for Herschel-Berkeley model, and the remodeling. So this progress failure. So basically, it varies exponentially with the shear strain at the bottom of the layer. And we have 3 K parameters. So this is basically the peak and the residue, and also the remodeling parameter. So the parameter I mentioned is difficult to quantify, because normally we don't know how brittle the material is. And we carry out the benchmark calibrations of Binklau against some well-known case studies. So in this calibration, basically, we want to say if we implement the shallow water equation properly in this Binklau software. And this very simple 1D dam bridge simulation. So we have 2 slopes, 0 slope and 2 degree slope. So the flow, so basically the water is 10 meter high and with a length of 1 kilometer. And basically these red colors are from analytical solutions, and these black curves are from our Binklau simulations. So they match with each other quite well. So that basically gave us confidence to use Binklau for water dam simulations if we have this kind of problem. And then we calibrate our Binklau simulation against a full-scale event. So this is a very well-known failure. Has been used for calibrations with many numerical simulations. So basically here we have a boundary deck is failing over a length of 140 meters, and the failure, the tailings run up perpendicular to the deck, and we didn't change any parameters. So we don't want to back calculate in this case. So we use the same parameter in the literature and to make the comparison more fair. And the analytical solution, basically they end up with 300 runout distance, and we end up with 370 meters. So it's about 20% longer than the case. And the reason for this perhaps is because we didn't consider any slope in this analysis, and we also have limitation in our Binklau simulation. We have only 1 uniform material here, but it also provides our confidence that the model is capable of modeling this full-scale event here. And then we are very confident of our model here. So then we do a Class A prediction for Feijiao analysis. And basically this Feijiao tailings failure, I think almost everybody's knowing this tailings dam failure. So basically the red colors here is the runout extent interpreted by our remote sensing images. And we end up with a very good match with the real failure from our simulations, and the arrival time is very comparable to our observation as well. So it takes about 1 hour, 1.5 hour or 2 hours for this failure. And when we look at our simulations at 2 hours, so we basically reach the river down here. And we are very interested in how this yield strength, the residual strength, is affecting our runout behavior. So that's why we carry out this sensitivity analysis to see the effect of residual shear strength on the runout behavior. So all this, the peak strength and the capital gamma value are calibrated based on our base knowledge here. As you can see here, so basically the maximal slide velocity is not quite impacted by the by the radial shear strength here. So basically, we end up with very similar maximal velocity along the failure path. But runout distance is decreasing with increasing with radial strength. So basically here, here is the velocity, and here is the time. So we end up with higher velocity for smaller residual strength. So basically, we end up with larger runout distance. And then we consider consequence analysis. So by using OpenStreetMap, we come up with the locations and the features of all these buildings here. And we are able to say how the runout of tailings material could impact on our buildings here. So basically, we have our deposit height, for instance, with time, and then we could implement our vulnerability curve. So basically, it's a function of deposit height, and then we come up with the vulnerability of all these buildings in the failure zone here. As another presentation of consequence, this could be carried out in terms of velocity as well. So we could assess vulnerability of buildings by using the correlation between the vulnerability of buildings and the flow velocity. So we have different velocities at different locations. We have higher velocity here. That means the building could be impacted heavily here. I think this brings to my last slide. In this slide, in this presentation, basically we want to emphasize that the risk assessment and probability analysis is an added value to our assessment and management of tailings facilities. But the main thing here is that we should emphasize the uncertainty in probability estimation and risk management to the stakeholders, but they need to understand the whole concept. They need to communicate with the public as well. So there's quite a few improvements we should carry out in the years to come. So thank you for your attention.
Thank you very much, Songchang, for your nice presentation about triggering and runout modeling. I may ask all the three speakers to join me here. So Songchang is here already, Scott, and Deep Anchor. Where is Deep? Oh, right. Sorry, I didn't see. Okay, so do we have questions from the audience? Curiosity. Susan, please. I can bring you the microphone.
It's a question for Scott. You did a back calculation using 4 different programs, Dan 3D and Flow 2D, 3D, and that's beautiful for research and such. Now, if you're a consultant, which one will you recommend and why? And I guess it's my deviated way of asking what were the results of the comparison. I know you like 3D, but why, if that's the one you recommend?
Thank you. I'm going to dodge that question, I think. Because Dan 3D is my program. So the quick answer is, of course, Dan 3D. So, but I don't think that's true. I think the best answer is the program that the modeler is most comfortable and experienced using at the present time. Because I think that all of the models that we looked at were capable of simulating these flows with the right input parameters. And to get the right input parameters takes a lot of judgment. And so I think a lot of it's in the modeler's hands. So really, we weren't looking at comparing models to try to figure out which one was better at doing the simulations. I think they all kind of have their own strengths and weaknesses. And we can get into the details. Some of them run extremely fast compared to others, and that's a consideration too, especially when you have limited budget for doing these kinds of analyses. But I think a lot of it right now is in the hands of the modelers. And in the hands of a good modeler, all of these models are capable. I know that doesn't answer your question, but that's my opinion.
It does, but if you're a consultant, would you limit yourself to only one modeling? Would you try?
I think like historically, that's been true. I think the modelers have their favorite model that they were trained on that they're comfortable using. But I see the consultants that we're working with now are interested actually in trying different models. So that's been one really nice outcome of this project is actually having 3 consulting companies working together. They become interested in the methods that each other are using and actually have been willing to try some new methods. And I know a couple of them are also dabbling in material point method as well. And of course, they'd be interested in Bing Claw too, I'm sure. Yeah.
There's another question. Jorge, please.
A quick follow-up on the previous question. Don't you think that using all models would be actually maybe a good practice to capture epistemic uncertainties? For example, when we do ground motion modeling, for example, there is also 4 or 5 models. Usually the approach we take is to use all of them and to put a weight on each one of them depending on how comfortable, or it's kind of expert judgment. Don't you think that could be I would say a recommended approach?
Yeah, I've thought about that too, because for climate modeling, it's very common, right, to use a weighted approach with multiple models. So I think that's common practice in other fields, but not very common in this application. I think a lot of it has to do with just the limited budget and time that consultants have to do these analyses. And so, because some of these models flow 3D, for example, if you want to do a fully 3D analysis, it may take a week to run something that you can run in 10 minutes on a 2D model like Dan 3D. I think that's really the constraint here is just, and maybe the consultants need to do a better job of getting enough budget to run multiple models, but I could see things going in that direction.
And a quick question for Deepankar is, on your presentation you showed, I believe, the acceleration was kind of 2.5 G, and the displacements were kind of relatively small. So I was curious on the very large acceleration. I mean, correct me if I'm wrong, but I think it was very large, and the small displacements. If you can comment on that, that would be great.
Yeah, very good observation. Actually, you see the high amplification has been mentioned, but it is over the depth. So it is not at a fixed level. So if you see from the ground level to 5-meter height, 10-meter height for the first phase, so different level of amplification. So what I have quoted over here is the average one. So you are right. If we go by the maximum number of amplification, then the corresponding displacement or settlement may look small, but actually it is referring to the total settlement based on the average amplification. So that is what we have obtained, and also analytically we have computed from the pseudodynamic method. Yeah. But yes, maximum amplification can bring more settlement also. Yeah.
Another question, Ramon, Verdugo, please.
You mentioned that you use vertical component as a half of the horizontal one. But that has one problem, that the peak acceleration are at the same time. And usually doesn't happen in the real earthquake. That's one question. So, and the second is you have very high acceleration. However, in your limited equilibrium analysis, you use a seismic coefficient of 0.15. So these two things are not talking among them.
Okay, good observation, I must say. The first one, what you have referred to, considering kV as half of kh, that is vertical acceleration, half of horizontal, is as per the codal provision. So our code suggests that you consider this one, but even I also don't believe or stick to that number, half of the horizontal one. It should be the realistic based on, as I said, how the ground motion for a site to be selected. So that is the real dynamic analysis. And the component which I have referred on that slide is essentially the code-based recommendation where it says the half one. And the second point, what you have mentioned about the peak ground acceleration, the selection. So there are 3 ways it has been again done. One is based on the code advised seismic zone-wise value. Another is for the synthetic time history, dynamic real analysis, what is the value? And the third one is the assumed value for that zone. So these three, there is a huge variation, as you have rightly observed. Now, people can always debate that which one to be considered. But of course, one can always go on the safer side or the conservative side of the design. But what we wanted to show that all the three aspects, whether you design with the code, with the real dynamic analysis, or a closed form solution, whatever dynamic solution is available, all three should give a safer tailing dam. So that's what. So it's a good observation that there is a variability in the value. Yeah, true.
Thank you.
Thank you very much.
Short question.
Yeah, sure.
In the run-out calculation, in our case, we always have two problems. It is not the model, but it's the decision. How much water we consider in the tailing. If we use too much water, I think this is really a large flow, and if we don't consider water, dry season, nothing happens sometimes. This is one factor, and the second factor is because the dam is supposed to be stable. Because it is stable, there is no failure, so we have to create the failure. And depend on the dimension of that bridge, also you will have much more tailing flowing or nothing. So what do you think about these two factors that are beyond the model that you are using to compute the runout?
Yeah, very good point. I mean, regarding the first question, this water problem. Yes, we always have a lot of waters in the tailings facilities. But for our simulations, we don't consider water at all. But we could consider the water by reducing or increasing the strength of this unified material. So basically, it's not only for water. If we have a layered soil or layered tailings dams materials, we only have, in our simulation, we only have one uniform layer. So we have to adjust our strength parameters in the simulation. And the second point, this is a very good point as well. I think also perhaps it's relevant to the question from Susan and Yusuke. So basically, the tailings dam or facility is standing there. So we don't really know how much material could flow. So this release volume. So basically, one effort or one study we are carrying out at the moment is to combine finite element analysis and MPM as well with our flow dynamic analysis. So by carrying out MPM or FEM analysis, you could identify potential failure. And then with a few sections, cross sections, you could come up with a reasonable release volume. I mean, for all this flow dynamic analysis, done 3D, beam cloud, and flow 2D, you have to interpret your release volume. So that's a limitation for our flow dynamic analysis. But if we combine FEM or MPM with our flow dynamic analysis, then we could have a full picture here.
Okay, I may have one question, curiosity myself, to ask to Scott. I was not quick enough to read on the axis, but one of the correlations was like outflow volume with, I thought it was like depositional area, something like that. My question is, usually runout is a function of tailings and material itself, failure modes, and topography downstream. So my question is, how reliable are these correlating outflow volume and depositional area, in your opinion?
Yeah, well, and that's shown in the scatter in that correlation. Obviously, there's a wide variability that's probably related to things like confinement downstream and composition of the tailings and all the factors that you mentioned, which is why we looked at trying to sort those data points in terms of other similarities and look at sub-correlations. Because it's such a sparse data set, I think we only had like 30 data points altogether. We couldn't say anything statistically about how those things sorted based on these other factors.
Yeah.
So we didn't take it that far, but I think it's an important point, and that's why, we would only recommend that method for a screening level analysis, or maybe looking at averages for a portfolio-wide or region-wide kind of application.
Okay, thank you very much. Okay, great. There is one question online. I think we can take it as a last one. And about runout modeling in order to handle all the uncertainties at play linked with material properties, saturation ratio, rheology, type of numerical model. It is essential to perform sensitivity analysis and to produce maps for all the considered scenarios. I think it's more like a comment than a question. Someone wants to comment about that?
I agree.
It's a comment out of a comment.
I think that's why the work that NGI is doing, looking at the probabilistic application, is really important, right? Because we do have to look at the different sub-scenarios in terms of sensitivity of volume, and we can see how that influences the runout results. So I think moving in a probabilistic direction is key.
Okay, then I thank you guys, you speakers, for this last session. And before leaving the venue here to the Nordic ICLD meeting, we have some communications to do. Okay, first is we can inform about day 3, the online attendees, that we are going to try and we are going to send a Teams meeting link so you can follow at least the first presentation. That is going to be on day 3. Of course, you cannot do the virtual tour of the labs, but then you will be also receive another link for the final summary, where we are going to summarize the discussion of the roundtables. So I think it's nice. So the workshop will continue also to day 3 for the people attending online. This was the first thing to mention. Second, we got some homeworks. Sparsha's got some homeworks. So if I can ask to put the last slides. Thank you very much.
Thank you.
Come back to the seat.
Yes. Thanks. Nice job.
Yes, presentation.
Yeah.
Thank you.
Good job.
Yeah. We are gonna ask you, all attendees, online and in person, to reply to these questions.
Yes. So it's not that we are done with the day and you can just go back, go around, have your dinner and relax. We have something for you because it's a workshop. So you're supposed to kind of think over things. And we kind of have these 2 polls, I would call it. So the first one talks about what are the technical challenges that tailings facilities kind of go through, and which technical aspects are actually important. So you have a set of 10 questions, and you need to kind of grade them from 1 to 5. 1 meaning that they are not so relevant, the technical aspect is not so relevant, and 5 is they're extremely relevant. And the other poll is basically, how can the mining industry or the tailings industry perform better? They're doing good in certain aspects. Probably there are certain aspects which they can do better. So here also we follow the same kind of gradation. 1 means we're not doing a good work. 5 is we are doing a good work. So basically we want to have your perspective from the place you come from, and also whether you come from the academia or you come from the industry. So it's going to be anonymous, so we're not going to judge you. You're not going to get any grades for it. So please be brave enough and be as sportive, as blunt, and as frank as you can be, because we are going to use the results of the poll for a roundtable discussion on the 3rd day in the NGI premises. So you've already also been sent the link via email. So if you can just check your emails, you also already have it via email. And the online participants also have it in the detailed email that was sent to them. So please try to fill up these forms as soon as you can, probably by tomorrow, so that we could analyze the results and have them ready for the discussion on the 3rd day at NGI. Yes.
Great. Yeah. And last thing is, if we can come here all together so we can take a photo now. Before, yes.
While you see, just before everything starts moving. So we will have a Nordic tailings network meeting now, just after we finish here. the idea was to have some. I think it's a manageable group. It's not. A lot of you come from outside the Nordic countries, so the idea was to have some group discussions. I think you've seen enough slides today. So my idea is that those who want to join, stay here, and then we go outside. The weather is beautiful, and then we sit down. It's like a restaurant bar thing outside, and we do it there.
I had you on the list, on the things to do, don't worry. Okay, if you can come all here for the photo. Okay, thank you for the people attending online. We'll reconvene tomorrow 8:45 Central European Summer Time. Yeah.